Have you ever wondered what it would be like to witness the ultimate prehistoric parade? Picture this. Massive creatures stretching as long as city buses, their distinctive flat beaks gleaming in the ancient sunlight, moving in thunderous herds across vast floodplains. These weren't just any dinosaurs. These were the superstars of the Late Cretaceous, the champions of plant-eating efficiency, the masters of family life in a world ruled by giants. Welcome to the extraordinary world of the duck-billed dinosaurs, where survival meant more than just avoiding sharp teeth and crushing jaws. In this epic journey, we're going to uncover the secrets behind one of the most successful dinosaur groups that ever walked the earth. We'll explore how these remarkable creatures conquered entire continents, developed some of the most sophisticated eating systems nature has ever devised, and created family structures that would make modern parents jealous. But here's what makes this story absolutely mind-blowing. These weren't primitive, simple-minded beasts stumbling through prehistoric swamps. Recent discoveries have revealed that duck-billed dinosaurs possessed some of the most advanced brains among all plant-eating dinosaurs, engineered complex social behaviors that rival modern mammals, and developed communication systems so intricate they could produce sounds we're only beginning to understand today. The scientific evidence we've uncovered over the past few decades completely transforms everything we thought we knew about these animals. From fossilized stomach contents that reveal their last meals to perfectly preserved skin impressions showing scales in stunning detail. From massive bone beds containing hundreds of individuals to nesting sites that tell stories of devoted parental care spanning millions of years. What we're about to explore together challenges every stereotype about dinosaur intelligence and social behavior. These creatures didn't just survive in one of Earth's most competitive ecosystems. They absolutely dominated it, spreading across multiple continents and adapting to environments ranging from lush tropical forests to harsh semi-arid landscapes. The journey begins roughly 100 million years ago, when the ancestors of duck-billed dinosaurs were taking their first evolutionary steps. But the real action starts during the Late Cretaceous period, about 80 million years ago, when these animals began their spectacular rise to dominance. This is when the duck-billed dinosaur parade truly began. And trust me, it's a story that will completely change how you think about prehistoric life. Let's start with the basics, because even the fundamentals of these creatures are absolutely fascinating. Duck-billed dinosaurs earned their nickname from the distinctive flat, broad shape of their snouts, which resembled the bills of modern waterfowl. But unlike actual duck bills, these structures were made of solid bone and designed for something far more sophisticated than dabbling in ponds. The scientific name for this group is Hadrosaur, and they represent one of the most diverse and successful families of herbivorous dinosaurs ever discovered. These weren't just big plant eaters wandering around prehistoric landscapes. They were evolutionary masterpieces, perfectly adapted machines that revolutionized how large animals could process vegetation. Think about the challenge these animals faced. In a world filled with massive predators like Tyrannosaurus rex and equally enormous plant-eating competitors like long-necked sauropods, duck-billed dinosaurs needed something special to carve out their niche. That something special turned out to be their incredible ability to process tough plant material with unprecedented efficiency. The key to their success lay in their mouths. While most dinosaurs had relatively simple teeth designed for basic cutting or grinding, duck-billed dinosaurs developed what paleontologists call dental batteries. These were complex arrangements of hundreds, sometimes nearly 1,000 individual teeth, all working together in perfect harmony to create the most effective plant processing system the dinosaur world had ever seen. But here's where it gets really interesting. These dental batteries weren't static structures. The teeth were constantly being replaced throughout the animal's lifetime, ensuring that their primary tool for survival remained sharp and effective. Imagine having a mouthful of self-sharpening tools that could handle everything from soft leaves to tough conifer needles, and you'll begin to understand the evolutionary advantage these creatures possessed. The sophistication doesn't stop there. Recent studies using advanced scanning techniques have revealed that duck-billed dinosaurs possessed cheek-like structures that could hold plant material in their mouths while they chewed. This might sound simple, but it represents a major evolutionary breakthrough that allowed them to extract maximum nutrition from their food. Now let's talk about their bodies, because the physical design of these animals tells an incredible story of adaptation and success. Most duck-billed dinosaurs were what scientists call facultative bipeds, meaning they could walk comfortably on either 2 legs or 4, depending on what the situation demanded. Young animals typically moved around on their hind legs, probably for speed and agility, while adults often walked on all 4s, especially when feeding. This flexibility and locomotion gave them tremendous advantages in their environment. When they needed to reach high vegetation, they could rear up on their hind legs like giant prehistoric giraffes. When they needed to move quickly to escape predators or migrate to new feeding grounds, they could drop down to all 4s and achieve impressive speeds despite their massive size. Speaking of size, these animals were genuinely enormous by any standard. While some species were relatively modest at around 4 to 5 meters in length, others grew to absolutely staggering proportions. The largest known duck-billed dinosaur reached lengths of 17 meters and weighed over 15 tons, making it one of the largest land animals that wasn't a long-necked sauropod. But perhaps the most fascinating aspect of duck-billed dinosaur anatomy was their incredible diversity in head crests and facial features. This is where the story becomes truly spectacular, because these weren't just random variations. Each different type of crest served specific purposes related to communication, species recognition, and social behavior. The duck-billed dinosaur family split into 2 major groups, and understanding this division is crucial to appreciating their full story. The first group, known as the flat-headed forms, lacked elaborate crests, but made up for it with other distinctive features like prominent nasal humps or unique bill shapes. The second group developed some of the most remarkable cranial ornaments ever seen in the animal kingdom. These crested forms possessed hollow, tube-like structures extending from their skulls that contain complex networks of nasal passages. Think of them as built-in musical instruments designed by millions of years of evolution to produce specific sounds for communication. Different species had different crest shapes, which means they could produce different sounds, allowing them to identify members of their own kind, even in environments filled with multiple duck-billed dinosaur species. The implications of this discovery are staggering. We're not talking about simple grunts or roars. These animals possess the anatomical equipment necessary for sophisticated acoustic communication, possibly including the ability to produce low-frequency calls that could travel for miles across ancient landscapes. Imagine the soundscape of the Late Cretaceous, filled with the haunting calls of massive herbivores communicating across vast distances. Recent computer modeling has even attempted to recreate these ancient sounds by analyzing the internal structure of fossilized crests. The results suggest that different species could produce distinctly different tones and frequencies, supporting the idea that acoustic communication played a major role in their social behavior. This brings us to one of the most exciting aspects of duck-billed dinosaur research: their social behavior and intelligence. For decades, paleontologists suspected that these animals lived in groups based on the discovery of multiple individuals buried together. But recent discoveries have revealed social structures far more complex than anyone imagined. We now know that duck-billed dinosaurs lived in herds that could contain hundreds or even thousands of individuals. These weren't just random gatherings of animals that happened to be in the same place at the same time. These were organized communities with evidence of cooperative behavior, shared nesting areas, and what appears to be communal care of young. The evidence for their intelligence is equally compelling. Studies of fossilized brain cases reveal that duck-billed dinosaurs possessed some of the most developed brains among plant-eating dinosaurs. Their cerebral hemispheres, the parts of the brain associated with complex behavior and learning, were significantly more advanced than those of most other dinosaur groups. This enhanced brain power translated into sophisticated behaviors that we're only beginning to understand. They appear to have engaged in seasonal migrations, traveling hundreds of miles between feeding and breeding grounds. They developed complex nesting behaviors that involved careful site selection, nest construction, and extended parental care that lasted for months or even years. The nesting sites themselves tell remarkable stories. In some locations, paleontologists have discovered what can only be described as dinosaur cities, with hundreds of nests arranged in organized patterns across vast areas. These sites show evidence of repeated use over multiple seasons, suggesting that duck-billed dinosaurs return to the same locations year after year, possibly following traditional migration routes passed down through generations. But what really sets duck-billed dinosaurs apart from other prehistoric animals is their incredible success in colonizing diverse environments. While many dinosaur groups remained restricted to specific types of habitats, duck-billed dinosaurs spread across virtually every continent except Australia, adapting to environments ranging from lush river valleys to harsh, semi-arid regions. This adaptability was the key to their evolutionary success. As climate conditions changed throughout the late Cretaceous, duck-billed dinosaurs evolved new species to match new environmental challenges. Some developed specialized feeding adaptations for life in coastal swamps. Others evolved features suited for browsing in highland forests or grazing in open plains. The fossil record reveals wave after wave of duck-billed dinosaur diversification, with new species appearing and spreading across vast geographic areas in relatively short periods of geological time. This pattern suggests not just passive adaptation to changing conditions, but active exploration and colonization of new territories by highly mobile, intelligent animals. By the end of the Cretaceous period, duck-billed dinosaurs had become the dominant large herbivores across much of the world. They had successfully competed with and largely replaced many other plant-eating dinosaur groups, establishing themselves as the undisputed champions of late Cretaceous ecosystems. Their success story represents one of the most remarkable examples of evolutionary triumph in the entire history of life on Earth. From humble beginnings as relatively simple plant eaters, they transformed themselves into sophisticated, intelligent social animals that dominated their world for millions of years. But this is just the beginning of their incredible story. As we continue our journey through the world of duck-billed dinosaurs, we'll discover how they developed their remarkable feeding strategies, explore the intimate details of their family lives, and uncover the secrets behind their extraordinary diversity and success. The evolutionary journey that led to duck-billed dinosaur supremacy is absolutely mind-blowing when you understand the challenges they overcame. These animals didn't just stumble into success. They engineered their way to the top through a series of brilliant biological innovations that would make modern engineers jealous. Let's dive into the feeding revolution that changed everything. Remember those dental batteries we talked about? Well, the story gets even more incredible when you realize how they actually worked. Picture this. Instead of having just a few large teeth like most dinosaurs, duck-billed dinosaurs packed their jaws with hundreds of smaller teeth arranged in precise rows. But here's the genius part. These teeth weren't all the same height. The arrangement created a natural grinding surface that worked like a biological food processor. As the upper and lower jaws came together, the teeth would slide past each other in a complex, shearing motion that could reduce the toughest plant material into easily digestible fragments. This wasn't simple chomping like you might see in other dinosaurs. This was sophisticated, coordinated mechanical processing that maximized the nutritional value extracted from every bite. What makes this even more remarkable is that different species developed slightly different tooth arrangements to handle specific types of vegetation. Some had dental batteries optimized for slicing through tough conifer needles. Others evolved systems better suited for grinding fibrous leaves or processing seeds and fruits. This specialization allowed multiple duck-billed dinosaur species to coexist in the same environments without directly competing for food resources. The efficiency of their feeding system was so superior that it fundamentally changed the balance of power in late Cretaceous ecosystems. Before duck-billed dinosaurs reached their peak, long-necked sauropods dominated most plant-eating niches. But sauropods were essentially living conveyor belts. They had to constantly consume massive quantities of low-quality vegetation because they couldn't process it very efficiently. Duck-billed dinosaurs turned this equation upside down. Their advanced dental systems allowed them to extract far more nutrition from the same amount of plant material. This meant they could maintain their enormous body size while spending less time eating and more time on other activities like socializing, migrating, and caring for their young. This feeding efficiency also opened up new ecological possibilities. While sauropods were mostly restricted to environments with abundant, easily accessible vegetation, duck-billed dinosaurs could thrive in more marginal habitats where food was scarcer or more difficult to process. This adaptability was crucial to their eventual global dominance. But the innovations didn't stop with their mouths. Duck-billed dinosaurs also developed sophisticated digestive systems that could handle the massive quantities of plant material they consumed. Fossil evidence suggests they had enlarged stomach regions where vegetation could be stored and processed by beneficial bacteria, much like modern ruminants. Some specimens have even been preserved with their last meals intact, providing incredible insights into their dietary preferences. These fossilized stomach contents reveal a surprisingly diverse menu that included ferns, conifer needles, seeds, fruits, and even rotting wood. The variety suggests these animals were opportunistic feeders that could adapt their diet based on seasonal availability and environmental conditions. Now, let's talk about something that will absolutely blow your mind: their family life. Recent discoveries have revealed that duck-billed dinosaurs weren't just successful feeders and travelers. They were devoted parents that invested enormous amounts of time and energy into raising their young. The nesting sites discovered by paleontologists paint a picture of prehistoric suburbia that's almost surreal in its organization. Imagine walking through a late Cretaceous landscape and encountering a vast plain covered with hundreds of carefully constructed nests, each one spaced exactly 7 meters apart, like houses in a planned community. These weren't random scrapes in the ground. Duck-billed dinosaur nests were engineered structures made of packed earth and arranged vegetation. Each nest could contain 30 to 40 eggs, roughly the size of modern ostrich eggs, arranged in precise circular or spiral patterns that maximize space while ensuring even incubation. But here's where it gets really fascinating. The parents didn't just lay their eggs and abandon them. Fossil evidence shows that adult duck-billed dinosaurs remained at the nesting sites throughout the incubation period, using rotting vegetation to generate the heat needed to keep their eggs at the proper temperature. This is remarkably similar to the nesting strategies used by some modern birds, but these dinosaurs were doing it 70 million years ago. When the babies hatched, they weren't immediately capable of independent survival. Unlike many reptiles that can fend for themselves from birth, duck-billed dinosaur hatchlings were essentially helpless. They had oversized eyes and shortened snouts compared to adults, features that scientists recognize as indicators of animals that require extended parental care. The adults responded to this need by bringing food directly to the nest, feeding their offspring until they were large and strong enough to join the herd. Fossil growth studies reveal that these young animals grew at absolutely staggering rates, increasing from 40 centimeters to over a meter in length during their first year of life. This rapid growth required enormous amounts of food and constant attention from the parents. The investment was so significant that it fundamentally shaped the social structure of duck-billed dinosaur communities. Adults that were caring for young couldn't migrate as freely or range as widely in search of food. So the entire herd structure had to accommodate these family responsibilities. The result was a complex social system that balanced the needs of individuals, families, and the larger community. During nesting season, herds would gather at traditional breeding grounds where hundreds or thousands of animals would establish their nests in massive colonies. During other times of the year, smaller family groups might split off to explore new feeding areas or follow seasonal migration routes. This social flexibility was another key to their success. Unlike animals locked into rigid social structures, duck-billed dinosaurs could adjust their group dynamics based on environmental conditions, food availability, and reproductive cycles. This adaptability allowed them to thrive in the face of changing climate conditions and environmental pressures. The evidence for their social intelligence extends beyond just nesting behavior. Bone beds containing multiple individuals show patterns that suggest coordinated group movements and mutual aid. Some fossil sites preserve animals of different ages and sizes together, indicating that herds included multiple generations and that knowledge was passed from older to younger individuals. The communication systems we discussed earlier played a crucial role in maintaining these complex social structures. The ability to produce and recognize specific sounds allowed duck-billed dinosaurs to coordinate group movements, warn of dangers, and maintain contact between individuals over large distances. Different species had distinctly different crest shapes and internal structures, which means each group could produce its own unique acoustic signatures. This prevented confusion in environments where multiple duck-billed dinosaur species lived in close proximity, ensuring that individuals could find and communicate with members of their own kind. The sophistication of their communication systems becomes even more impressive when you consider the acoustic challenges of their environment. Late Cretaceous landscapes were filled with the sounds of numerous other dinosaur species, environmental noise from wind and weather, and the natural background sounds of dense forests and open plains. To be effective in such conditions, duck-billed dinosaur calls needed to be both distinctive and powerful. Computer modeling based on fossilized crest structures suggests these animals could produce low-frequency sounds that could travel for miles, allowing herds to maintain contact even when spread across vast territories. Some species appear to have been capable of producing multiple different types of calls, possibly indicating a complex vocal repertoire that included alarm calls, mating calls, territorial announcements, and social contact sounds. This level of acoustic sophistication rivals that of many modern mammals and birds. The intelligence required to develop and use such communication systems points to cognitive abilities that far exceed what we traditionally associate with dinosaurs. These weren't simple, instinct-driven creatures. They were thinking, learning, communicating animals that could adapt their behavior based on experience and changing circumstances. As we explore deeper into the world of duck-billed dinosaurs, the picture that emerges is of animals that were remarkably similar to modern social mammals in their complexity and sophistication. They lived in organized communities, cared for their young with dedication that lasted for years, communicated through elaborate systems of sounds and visual displays, and adapted their behavior to meet the challenges of their environment. But perhaps most impressively, they did all of this while maintaining their position as the dominant large herbivores in some of the most competitive ecosystems Earth has ever seen. The Late Cretaceous was a time of enormous predators, fierce competition for resources, and rapidly changing environmental conditions. Yet duck-billed dinosaurs not only survived in this challenging world, they absolutely thrived. Their success wasn't just a matter of being in the right place at the right time. It was the result of millions of years of evolutionary refinement that produced animals perfectly adapted to their world. Every aspect of their anatomy, behavior, and social organization was fine-tuned to maximize their survival and reproductive success. From their revolutionary feeding systems that could extract maximum nutrition from available vegetation, to their sophisticated social structures that balanced individual needs with group benefits, to their advanced communication systems that allowed coordination across vast distances, duck-billed dinosaurs represented the pinnacle of herbivorous dinosaur evolution. As we continue to uncover new fossil evidence and apply advanced analytical techniques to existing specimens, our understanding of these remarkable animals continues to grow. Each discovery adds new details to the portrait of creatures that were far more complex, intelligent, and successful than anyone could have imagined just a few decades ago. The duck-billed dinosaur parade wasn't just a collection of large plant-eating animals wandering through prehistoric landscapes. It was a sophisticated civilization of thinking, feeling, communicating beings that dominated their world through intelligence, cooperation, and remarkable evolutionary innovation. The diversity of duck-billed dinosaurs reaches truly staggering proportions when you examine the incredible range of species that evolved across different continents and time periods. We're talking about a family tree so complex and varied that new species are still being discovered and described by paleontologists around the world on a regular basis. Let me paint you a picture of just how spectacular this diversity became. In North America alone, dozens of different duck-billed dinosaur species roamed the landscape during the Late Cretaceous. Each one was perfectly adapted to its specific environment and ecological niche. From the massive plains-dwelling giants that could reach the size of modern elephants, to smaller, more agile forest browsers that navigated dense woodland environments. But here's where it gets absolutely mind-blowing. The crest variations alone represent one of the most remarkable examples of evolutionary creativity in the entire fossil record. Some species developed crests that looked like elegant trumpets, curving gracefully backward from their skulls in smooth, aerodynamic arcs. Others evolved crests that resembled ancient battle axes, with sharp, angular profiles that must have created dramatically different acoustic properties. The most spectacular examples possessed crests that were essentially living musical instruments. These hollow, tube-like structures contained intricate networks of air passages that could produce sounds ranging from deep, resonant bass notes to higher-pitched calls that could cut through the ambient noise of their environment. Imagine standing in a late Cretaceous forest and hearing the haunting melodies of these ancient giants echoing across the landscape. Recent discoveries have revealed species with crests so unique that they challenge our understanding of what was possible in dinosaur evolution. Some possessed multiple chambers within their cranial ornaments, suggesting they could produce complex harmonies or even modify their calls in real time by controlling airflow through different passages. The geographic distribution of these diverse species tells an equally fascinating story. As continents drifted apart and climate patterns shifted throughout the late Cretaceous, duck-billed dinosaur populations became isolated in different regions. This geographic separation triggered explosive evolutionary radiation, with each isolated population developing its own unique characteristics and adaptations. In Asia, duck-billed dinosaurs evolved some of the most extreme cranial ornaments ever discovered. Species with crests shaped like elaborate fans, others with forward-projecting spikes that resembled medieval jousting helmets, and still others with ornate multi-chambered structures that must have produced incredibly complex acoustic signatures. European duck-billed dinosaurs, meanwhile, developed their own distinctive features as they adapted to the unique environmental conditions of their island habitats. Some appear to have undergone dwarfing, evolving smaller body sizes as they adapted to limited resources on prehistoric islands. Others developed specialized feeding adaptations that allowed them to exploit plant resources unavailable to their larger relatives. Perhaps most surprisingly, duck-billed dinosaurs even made it to South America, where they arrived relatively late in the Cretaceous and rapidly diversified to fill available ecological niches. These southern pioneers evolved their own unique characteristics, adapting to the distinct climate and vegetation patterns of the southern continent. The success of this global expansion wasn't just a matter of luck or favorable circumstances. It required remarkable adaptability and intelligence that allowed these animals to colonize new environments, establish viable breeding populations, and compete successfully with existing fauna. Consider the challenges involved in establishing a population in a completely new environment. The colonizing animals had to locate suitable food sources, identify appropriate nesting sites, avoid new predators they had never encountered before, and establish social structures that could function in unfamiliar territory. The fact that duck-billed dinosaurs accomplished this feat repeatedly across multiple continents and diverse environmental conditions speaks to cognitive abilities and behavioral flexibility that rival those of the most successful modern mammals. But the story of duck-billed dinosaur diversity isn't just about different species adapting to different environments. Within individual species, we see remarkable variation in size, crest development, and other features that suggest complex social dynamics and individual recognition systems. Fossil evidence indicates that males and females of many species had distinctly different crest sizes and shapes, a phenomenon known as sexual dimorphism. Males typically possessed larger, more elaborate crests, which were probably used in courtship displays and competitions for mates. This suggests mating systems that involved complex behavioral displays and possibly even ritualized combat between competing males. The implications for their social behavior are staggering. Animals that invest heavily in elaborate display structures typically have sophisticated mating systems that require advanced cognitive abilities. Males need to assess the quality of competitors and potential mates. Females need to evaluate the fitness of potential partners, and both sexes need to engage in complex behavioral interactions that determine reproductive success. Recent studies of growth patterns in fossilized bones revealed that crest development was closely tied to sexual maturity. Young animals had small, simple crests that grew larger and more elaborate as they reached breeding age. This pattern suggests that crest size and shape served as honest signals of individual fitness and reproductive readiness. The energy investment required to grow and maintain these elaborate cranial ornaments was enormous. The bone tissue alone required significant calcium and other nutrients, while the complex internal structures demanded precise developmental control. Animals that could successfully develop and maintain impressive crests were advertising their superior access to resources and their genetic quality to potential mates. This sexual selection pressure drove the evolution of increasingly elaborate and diverse crest forms across different species and geographic regions. Like the tail feathers of peacocks or the antlers of deer, duck-billed dinosaur crests became evolutionary arms races, where individuals competed to produce the most impressive displays. The acoustic properties of these crests added another layer of complexity to their mating systems. Different species could produce distinctly different sounds, but within species, individual variation in crest size and shape probably created unique acoustic signatures that allowed animals to recognize specific individuals by their calls. This individual recognition capability would have been crucial for maintaining stable social relationships within large herds. Animals that could remember and identify dozens or even hundreds of other individuals could form alliances, recognize family members, and maintain complex social hierarchies that enhanced group cooperation and survival. The fossil record preserves tantalizing glimpses of these social interactions. Some bone beds contain individuals with healed bite marks and other injuries that suggest non-lethal conflicts between members of the same species. These weren't predator attacks or accidental injuries. They were the results of social interactions that involved physical contact, but stopped short of causing fatal damage. This pattern is consistent with modern animals that engage in ritualized combat or dominance displays. The ability to resolve conflicts without killing potential mates or valuable group members represents an advanced form of social behavior that requires significant cognitive sophistication. The healing patterns on these fossilized injuries also provide insights into duck-billed dinosaur social behavior. Animals with serious wounds that healed completely must have received care and protection from other group members during their recovery period. This suggests cooperative behaviors and mutual aid that extended beyond just parent-offspring relationships. Some fossil sites preserve evidence of what appear to be group activities that required coordination and planning. Mass death assemblages show hundreds of individuals that died together, possibly while attempting to cross flooded rivers during seasonal migrations, or while gathered at traditional feeding or breeding sites. The logistics of coordinating movements for such large groups would have required sophisticated communication systems and leadership structures. Modern animal groups that successfully coordinate mass migrations typically rely on experienced individuals who know traditional routes and timing, combined with communication systems that can maintain group cohesion across large distances and challenging terrain. Duck-billed dinosaurs possessed all the anatomical and behavioral tools necessary for such coordination. Their advanced acoustic communication systems could maintain contact between widely dispersed individuals. Their enhanced cognitive abilities could support the learning and memory required to follow traditional routes, and their flexible social structures could accommodate the leadership and cooperation necessary for group decision-making. The seasonal timing of many of these mass death events suggests that duck-billed dinosaurs followed regular migration patterns that were synchronized with environmental cycles. This kind of temporal precision requires internal biological clocks that can track seasonal changes and trigger appropriate behavioral responses at the right times. Modern migratory animals achieve this synchronization through complex interactions between environmental cues like day length and temperature, internal hormonal cycles, and learned behaviors passed down through generations. The fact that duck-billed dinosaurs appear to have possessed similar capabilities indicates a level of physiological and behavioral sophistication that approaches that of modern mammals and birds. The energy demands of these migrations were enormous, moving hundreds of kilometers while supporting massive body weights required careful timing to ensure adequate food resources along migration routes. Animals that mistimed their movements or chose poor routes would have faced starvation or exhaustion that could prove fatal. Success in this challenging lifestyle required not just individual fitness, but group knowledge that could only be maintained through cultural transmission of information from experienced to inexperienced individuals. Young animals had to learn migration routes, timing cues, feeding locations, and danger recognition from their elders. This cultural dimension of duck-billed dinosaur behavior represents perhaps the most sophisticated aspect of their social evolution, the ability to accumulate and transmit knowledge across generations allows animal populations to adapt to environmental challenges much more rapidly than genetic evolution alone. Evidence for this cultural transmission comes from the consistency of migration routes and nesting site locations across multiple generations. Fossil sites that show repeated use over thousands of years indicate that duck-billed dinosaur populations maintain traditional behaviors and locations across time scales far longer than any individual lifetime. The precision required to relocate specific sites year after year, sometimes across hundreds of kilometers of terrain, demands navigational abilities and memory systems of remarkable sophistication. Modern animals that accomplish similar feats typically rely on multiple navigation systems, including celestial cues, magnetic field detection, landmark recognition, and olfactory trails. Duck-billed dinosaurs possess the brain structure necessary to support such complex navigation systems. Their enlarged cerebral hemispheres contained the neural hardware required for spatial memory, route learning, and multisensory integration. Their advanced sensory systems could detect and process the environmental cues necessary for accurate long-distance navigation. But perhaps most importantly, they possessed the social structures that could maintain and transmit this navigational knowledge across generations. Young animals that learned migration routes from experienced adults could eventually become the leaders who guided future generations, creating an unbroken chain of cultural knowledge that persisted for millions of years. This combination of individual intelligence, social cooperation, and cultural transmission created a feedback loop that accelerated duck-billed dinosaur evolution and adaptation. Populations that developed more effective social behaviors and knowledge systems gained significant advantages over their competitors, driving the evolution of increasingly sophisticated cognitive and social capabilities. The result was a group of animals that represented the pinnacle of dinosaurian social evolution. They achieved levels of behavioral complexity, communication sophistication, and group coordination that wouldn't be seen again until the evolution of advanced mammals and birds tens of millions of years later. Their success wasn't just measured in individual survival or reproductive success. It was measured in their ability to create stable, multi-generational communities that could adapt to changing environmental conditions while maintaining their essential social and cultural characteristics. This community-level success allowed duck-billed dinosaurs to weather environmental challenges that drove many other dinosaur groups to extinction. When climate patterns shifted or new predators appeared, duck-billed dinosaur communities could respond through behavioral adaptation and cultural innovation rather than waiting for slower genetic changes. The evidence suggests they were remarkably successful at this adaptive process. Throughout the Late Cretaceous, as environmental conditions became increasingly challenging and extinction pressures mounted for many other dinosaur groups, duck-billed dinosaurs continued to diversify and expand their geographic range. They were among the last dinosaur groups to disappear at the end of the Cretaceous, and their fossils from this final period show no signs of decline or stress. Right up until the asteroid impact that ended the age of dinosaurs, duck-billed dinosaurs were thriving, evolving new species, and maintaining their position as the dominant large herbivores across multiple continents. Their ultimate extinction wasn't the result of evolutionary failure or competitive displacement. It was simply the consequence of a catastrophic environmental change so severe that no large terrestrial animal could survive it. In a world without that cosmic accident, duck-billed dinosaurs might well have continued their evolutionary success story for millions more years. The legacy of their remarkable achievements lives on in the fossil record, providing us with detailed insights into what was possible in terms of dinosaur intelligence, social behavior, and evolutionary success. Every new discovery adds to our understanding of these extraordinary animals and their sophisticated prehistoric civilization. Their story challenges every assumption about dinosaur capabilities and provides a fascinating glimpse into alternative pathways that evolution might have taken. In a very real sense, duck-billed dinosaurs represent one of evolution's greatest success stories, a testament to the power of intelligence, cooperation, and social innovation in the natural world. As we continue to study their fossils and analyze their behavior, we gain not just insights into prehistoric life, but valuable perspectives on the fundamental principles that drive evolutionary success in complex, challenging environments. The duck-billed dinosaur parade continues to march through our understanding, revealing new wonders with every step. The sheer variety of duck-billed dinosaur species becomes even more remarkable when you examine the specific adaptations that allowed them to thrive in different environments across the globe. We're looking at evolutionary innovation on a scale that's almost impossible to comprehend, with each species representing a unique solution to the challenges of survival in late Cretaceous ecosystems. Let's explore some of the most extraordinary examples, because the diversity within this group will absolutely blow your mind. In the coastal regions of what is now North America, massive species like Corythosaurus evolved to become true giants of their world. These colossal animals stretched 17 meters from nose to tail and weighed over 15 tons, making them larger than many of the famous long-necked sauropods that dominated earlier periods. But size wasn't their only advantage. These giants possessed skulls that were marvels of biological engineering, measuring over 1.5 meters in length. Their enormous beaks could crop vast quantities of vegetation with each bite, while their dental batteries contained nearly 1,000 individual teeth working in perfect coordination to process this massive intake of plant material. The mechanical advantage of their jaw muscles was so significant that they could generate crushing forces capable of breaking down the toughest conifer branches and fibrous plant stems. This wasn't just brute force feeding. This was precision engineering, applied to the problem of extracting maximum nutrition from challenging plant materials. These coastal giants lived in environments that presented unique challenges. The fluctuating water levels, seasonal flooding, and salt-tolerant vegetation of their habitats required specialized adaptations that set them apart from their inland relatives. Their robust limb bones and broad feet were perfectly designed for walking across soft, muddy substrates without sinking. Evidence suggests they were excellent swimmers, capable of crossing rivers and navigating coastal waterways with ease. This aquatic ability opened up feeding opportunities unavailable to purely terrestrial species, allowing them to access marsh plants and aquatic vegetation that provided different nutritional profiles than upland forests. Moving inland, we encounter species that evolved completely different survival strategies. The famous Hadrosaurus represents the pinnacle of plains-dwelling duck-billed dinosaur evolution, with adaptations that allowed massive herds to migrate across vast continental distances in search of seasonal food resources. These migrations weren't random wanderings. They were precisely timed, coordinated movements that required remarkable navigational abilities and social organization. Fossil evidence suggests herds containing thousands of individuals would travel hundreds of kilometers following traditional routes that had been established over countless generations. The energy requirements for such massive movements were staggering. Adult Edmontosaurus weighed several tons each, and moving these enormous bodies across continental distances required careful timing to ensure adequate food supplies along migration corridors. The animals had to coordinate their movements not just with seasonal changes in vegetation, but with the reproductive cycles that determined when they could afford to expend energy on travel versus caring for young. Their success in this challenging lifestyle is evident from their widespread distribution across North America. Edmontosaurus fossils have been found from Alberta to New Mexico, indicating migration routes that spanned the entire continent. The consistency of their anatomical features across this vast range suggests these weren't separate populations, but components of a single, interconnected migratory system. But perhaps even more impressive than these continental giants were the species that colonized more challenging environments. In what is now Montana and surrounding regions, Parasaurolophus evolved distinctive paddle-shaped crests that served multiple functions in their highland forest habitats. These solid crests were completely different from the hollow trumpet-like structures of their relatives. Instead of producing sounds, they served as visual displays and possibly as tools for pushing through dense vegetation. The flat, broad surface could have been used to part branches and undergrowth, allowing these animals to forage in forest environments that would have been inaccessible to species with more delicate cranial ornaments. One of the most remarkable Parasaurolophus specimens ever discovered provides unprecedented insights into duck-billed dinosaur biology. This incredibly preserved individual, nicknamed Leonardo, represents one of the finest dinosaur mummies ever found, complete with detailed skin impressions and fossilized stomach contents. The preservation is so extraordinary that scientists can examine individual scales across the animal's body, revealing patterns of skin texture that varied depending on body location and function. Areas subject to more wear and abrasion had thicker, more robust scales, while regions requiring flexibility had smaller, more pliable skin structures. The stomach contents are equally revealing, containing identifiable plant fragments that provide direct evidence of feeding behavior. The mixture includes ferns, conifer needles, and various other plant materials, confirming that these animals were selective feeders that chose specific plant types based on nutritional content and seasonal availability. This level of preservation allows us to reconstruct not just what these animals looked like, but how they lived, what they ate, and how they interacted with their environment in ways that skeletal remains alone could never reveal. It's like having a snapshot of daily life in the Late Cretaceous, frozen in time for our examination. The crested species present an entirely different category of evolutionary achievement. These animals developed some of the most sophisticated communication systems ever discovered in the fossil record, with cranial structures that functioned as complex acoustic instruments designed for long-distance social coordination. Parasaurolophus stands out as perhaps the most acoustically advanced of all duck-billed dinosaurs. Their elegant curved crests contained intricate networks of air passages that could produce haunting, trumpet-like calls audible across vast distances. Computer modeling, based on fossilized specimens, suggests these animals could generate sounds and frequency ranges that would have been perfect for long-distance communication in their forest environments. Different Parasaurolophus species possessed crests of varying lengths and curvatures, each producing distinctly different acoustic signatures. This allowed multiple species to coexist in the same regions without confusion, as each maintained its own unique vocal identity that prevented mating errors and territorial conflicts. The sophistication of their acoustic systems becomes even more impressive when you consider the precision required for their construction. The internal air passages had to be perfectly sized and shaped to produce the desired frequencies, while the external crest form had to balance acoustic function with structural strength and aerodynamic efficiency. Recent discoveries have even suggested that some specimens preserve evidence of soft tissue structures around their crests, possibly including inflatable air sacs that could have modified their acoustic properties in real time. Imagine these animals being able to fine-tune their calls by inflating or deflating specialized structures, creating even more complex and varied communication possibilities. The social implications of such advanced communication systems are staggering. Animals capable of producing and recognizing complex acoustic signatures could maintain detailed social relationships across large herds, coordinate group movements with precision, and transmit information about food sources, dangers, and environmental conditions over considerable distances. But the crested forms represent just one branch of duck-billed dinosaur acoustic evolution. The flat-headed species developed their own sophisticated communication strategies that relied more on visual displays and shorter-range vocalizations, optimized for close quarters social interactions. Species like Gryposaurus possess prominent nasal humps that could have supported inflatable soft tissue structures for visual signaling. These displays would have been particularly effective during face-to-face encounters, allowing individuals to communicate dominant status, reproductive readiness, and other social information through controlled inflation and coloration changes. The diversity of communication strategies across different duck-billed dinosaur groups suggests that social complexity reached extraordinary levels in late Cretaceous ecosystems. Different species weren't just occupying different ecological niches based on feeding preferences or habitat requirements. They were also partitioning the social and acoustic landscape, developing unique communication systems that minimized interference while maximizing the effectiveness of intraspecies coordination. This level of social organization required cognitive abilities that approached those of modern social mammals. The ability to recognize and respond appropriately to dozens of different acoustic and visual signals while maintaining awareness of environmental conditions and group dynamics, demands sophisticated neural processing that was clearly present in these remarkable animals. The evidence for their intelligence extends far beyond just communication systems. Detailed studies of fossilized brain cases reveal enlarged regions associated with sensory processing, memory formation, and behavioral coordination. These weren't simple, instinct-driven creatures responding mechanically to environmental stimuli. They were thinking, learning animals capable of adapting their behavior based on experience and changing circumstances. The complexity of their social structures becomes even more apparent when we examine their nesting behaviors and parental care strategies. The organized nesting colonies discovered at sites like Egg Mountain in Montana represent some of the most sophisticated breeding systems ever documented in the dinosaur fossil record. These weren't random gatherings of animals that happened to nest in the same area. They were carefully planned communities with precise spacing between nests, coordinated timing of reproductive activities, and evidence of cooperative behaviors that extended across family groups and possibly entire herds. The nests themselves were engineering marvels, constructed with rim walls that provided protection from flooding and predators, lined with vegetation that generated heat through decomposition and positioned to optimize drainage and sun exposure. The precision of their construction indicates that nest-building behavior was learned and refined through experience, with successful techniques being passed down through generations. The eggs within these nests were arranged in specific patterns that maximize space utilization while ensuring even incubation temperatures. The spiral and circular arrangements found in many nests represent optimal solutions to the geometric problem of packing large numbers of spherical objects into circular spaces, suggesting mathematical intuition that guided their construction. But perhaps most remarkably, the evidence indicates that parental care continued long after hatching, with adults bringing food to helpless young and providing protection from predators for extended periods. This level of investment in offspring represents a major departure from typical reptilian reproductive strategies and suggests parental behaviors more similar to those of modern birds and mammals. The rapid growth rates documented in juvenile specimens required enormous energy inputs that could only have been sustained through dedicated parental provisioning. Young animals increase their body length by over 200% during their first year of life, a growth rate that rivals that of modern large mammals and indicates metabolic capabilities far more advanced than traditional reptilian standards. This intensive parental care created strong selective pressures for enhanced cognitive abilities in both parents and offspring. Parents needed to recognize their own young among hundreds of similar individuals, assess their nutritional needs, and coordinate feeding activities with mates and possibly other adults. Young animals needed to recognize their parents, communicate their needs effectively, and learn the complex behaviors necessary for eventual independence. The social bonds formed during this extended period of parental care probably persisted throughout life, creating networks of related individuals that could cooperate in feeding, migration, and protection activities. These family-based social structures would have provided the foundation for the complex herd dynamics that characterized duck-billed dinosaur communities. Evidence from bone beds containing multiple generations suggests that these family groups remained cohesive over extended periods, with grandparents, parents, and offspring traveling and feeding together in multi-generational units. This kind of social stability requires long-term memory, individual recognition capabilities, and behavioral flexibility that indicates cognitive sophistication approaching that of modern elephants or cetaceans. The coordination required for large-scale migrations by these multi-generational groups would have been extraordinary. Imagine the logistics of moving thousands of animals across hundreds of kilometers while maintaining family group integrity, ensuring adequate food supplies for individuals of different ages and sizes, and coordinating timing to arrive at breeding grounds at optimal times. The success of duck-billed dinosaurs in accomplishing these feats repeatedly across multiple continents and varying environmental conditions represents one of the most remarkable achievements in the history of life on Earth. They didn't just survive in challenging environments. They created sophisticated social systems that allowed them to thrive and dominate their ecosystems for millions of years. Their expansion across global landscapes tells an incredible story of adaptive radiation and evolutionary innovation. As continents drifted apart and climate patterns shifted throughout the Late Cretaceous, duck-billed dinosaur populations found themselves in increasingly diverse environments that demanded new survival strategies. The colonization of South America represents perhaps their most impressive biogeographic achievement. These animals somehow crossed significant oceanic barriers to establish populations on a continent where they had never existed before, then rapidly diversified to fill available ecological niches in competition with existing fauna. The South American species that evolved from these pioneering populations developed their own unique characteristics, including specialized feeding adaptations for the distinctive vegetation of southern latitudes and modified social behaviors suited to different environmental pressures. The speed of this adaptive radiation suggests remarkable behavioral flexibility and genetic potential for rapid evolutionary change. Similar stories played out across Asia, Europe, and other regions as duck-billed dinosaur populations encountered new environments and evolutionary challenges. Each colonization event triggered bursts of speciation and adaptation that produced unique solutions to local environmental conditions. The diversity that resulted from these global expansion events created ecosystems of unprecedented complexity. In some regions, multiple duck-billed dinosaur species coexisted in the same habitats, each occupying slightly different ecological niches based on feeding preferences, body size, communication strategies, and social behaviors. This level of species packing required extraordinary precision in resource partitioning and behavioral differentiation. Species that were too similar in their ecological requirements would have competed directly, leading to competitive exclusion of the less efficient forms. The fact that multiple species could coexist successfully indicates that they evolved highly specific adaptations that minimized direct competition. The acoustic partitioning mentioned earlier was just one aspect of this behavioral differentiation. Species also divided up feeding resources based on plant preferences, feeding heights, seasonal timing, and processing capabilities. Some specialized in tough, fibrous materials that required powerful jaw muscles and robust dental batteries. Others focused on softer, more nutritious plant parts that could be processed more efficiently but were available in smaller quantities. Temporal partitioning also played a role, with different species being active at different times of day or seasons. Some evidence suggests that certain species were primarily crepuscular, feeding during dawn and dusk hours when competition was reduced and environmental conditions were optimal for their particular feeding strategies. The complexity of these ecological relationships created feedback loops that drove continued evolutionary innovation. As species became more specialized in their ecological roles, they also became more efficient at exploiting their particular resources, which allowed for larger population sizes and more extensive geographic distributions. The success of this specialization strategy is evident from the fossil record, which shows continued diversification and expansion of duck-billed dinosaur species right up until the end of the Cretaceous period. Rather than reaching some kind of evolutionary plateau, these animals continued to innovate and adapt, suggesting that their evolutionary potential was far from exhausted when the asteroid impact ended their reign. The tragic irony of their extinction is that it occurred at the peak of their evolutionary success. Duck-billed dinosaurs had achieved a level of ecological dominance and adaptive sophistication that positioned them perfectly for continued evolutionary success under normal environmental conditions. Their sophisticated social systems, advanced communication capabilities, flexible behavioral repertoires, and efficient physiological adaptations represented the culmination of millions of years of evolutionary refinement. They had solved the major challenges of large-bodied herbivorous existence and created sustainable population systems that could persist across changing environmental conditions. The diversity and sophistication achieved by duck-billed dinosaurs provides crucial insights into the potential pathways of evolution and the levels of complexity that can emerge through natural selection. Their story demonstrates that intelligence, social cooperation, and behavioral flexibility can be just as important as physical adaptations in determining evolutionary success. Their legacy continues to influence our understanding of dinosaur biology and evolution. Every new discovery adds to the growing body of evidence that dinosaurs were far more sophisticated and behaviorally complex than previously imagined. The duck-billed dinosaur parade marches on through our scientific understanding, revealing new wonders and challenging old assumptions with every fossil that emerges from the rocks. As we continue to study these remarkable animals, we gain not just knowledge about prehistoric life, but insights into the fundamental processes that shape evolution and determine success in complex, competitive environments. The lessons learned from duck-billed dinosaurs continue to inform our understanding of modern ecosystems and the principles that govern life on Earth. Their story serves as a powerful reminder of both the incredible creativity of evolution and the vulnerability of even the most successful species to catastrophic environmental change. In celebrating their achievements, we also acknowledge the precious nature of the evolutionary innovations that continue to unfold around us today. The duck-billed dinosaur parade may have ended 66 million years ago, but their influence on our understanding of life continues to grow with each new discovery and analysis. They remain among the most fascinating and instructive examples of evolutionary success in the entire history of our planet. The technological revolution that allowed duck-billed dinosaurs to achieve such extraordinary success wasn't just limited to their feeding systems and communication abilities. These animals developed what can only be described as prehistoric biotechnology, with anatomical innovations that solve complex engineering problems through millions of years of evolutionary refinement. Consider the biomechanics of their locomotion systems, the ability to seamlessly transition between bipedal and quadrupedal movement required sophisticated musculoskeletal adaptations that modern engineers are still trying to fully understand. Their hip and leg bones were designed with attachment points for muscle groups that could rapidly redistribute the animal's center of gravity depending on the situation. When they needed speed, perhaps to escape predators or chase down premium feeding spots during seasonal abundance, they could rear up on their powerful hind limbs and achieve impressive velocities despite their massive size. The muscle architecture required for this transformation was incredibly complex, with overlapping systems that could work together for quadrupedal stability, or independently for bipedal locomotion. But here's where it gets absolutely fascinating. The bone density and internal structure of their limb bones reveals that these transitions weren't occasional emergency maneuvers. They were regular, routine parts of daily life that their entire skeletal system was optimized to support. X-ray analysis of fossilized bones shows stress patterns that indicate frequent switching between different locomotion modes throughout their lives. This flexibility provided enormous advantages in diverse environments. In dense forests, bipedal movement allowed them to navigate between closely spaced trees and reach elevated food sources. In open plains, quadrupedal movement provided stability and endurance for long-distance travel. In aquatic environments, their swimming abilities opened up feeding opportunities that were completely unavailable to more rigid locomotion specialists. The neural coordination required for such complex movement patterns points to sophisticated motor control systems in their brains. Modern animals that can switch between different locomotion modes typically possess enlarged cerebellum regions responsible for balance and coordination. Fossil evidence suggests duck-billed dinosaurs had similarly developed brain regions that could manage these complex biomechanical transitions. Their success in mastering these locomotion challenges allowed them to exploit environments that were inaccessible to other large dinosaurs. While most gigantic herbivores were restricted to specific habitat types by their locomotion limitations, duck-billed dinosaurs could thrive in forests, plains, wetlands, and coastal regions with equal facility. This environmental versatility became crucial during periods of climate change and environmental instability that characterized much of the late Cretaceous. As sea levels fluctuated and vegetation patterns shifted, many dinosaur species found themselves trapped in shrinking habitat patches. Duck-billed dinosaurs could simply move to new environments and adapt their behavior to exploit whatever resources were available. The physiological innovations that supported their active lifestyles were equally remarkable. Evidence from bone histology studies suggests that many species maintained metabolic rates that were significantly higher than typical reptilian standards. This enhanced metabolism provided the energy necessary for their complex social behaviors, long-distance migrations, and rapid growth rates. But maintaining high metabolic rates creates its own challenges, particularly in terms of thermoregulation. Large animals have difficulty dissipating excess heat, and overheating can be fatal for active creatures in warm climates. Duck-billed dinosaurs solved this problem through a combination of behavioral and anatomical adaptations that rival the cooling systems of modern large mammals. Their elaborate cranial crests weren't just communication devices, they also functioned as sophisticated heat exchange systems, with blood vessels running through the hollow spaces that could dissipate excess body heat through controlled blood flow. Different crest shapes provided different cooling capacities, allowing species to fine-tune their thermal regulation based on their specific environmental challenges. Some species developed additional cooling mechanisms, including enlarged nasal passages that could evaporate moisture for cooling, similar to the panting systems used by modern mammals. The complexity of these integrated cooling systems indicates that thermoregulation was a major evolutionary pressure that shaped many aspects of duck-billed dinosaur anatomy. The energy demands of their lifestyles also required extraordinary digestive efficiency. Recent analysis of coprolites and fossilized gut contents reveals digestive systems that could extract maximum nutrition from plant materials through multiple processing stages. Like modern ruminants, they appears to have maintained symbiotic relationships with beneficial bacteria that could break down cellulose and other complex plant compounds. The sophistication of these digestive partnerships suggests coevolution between duck-billed dinosaurs and their intestinal microbes that lasted for millions of years. This kind of stable mutualistic relationship requires precise biochemical coordination and represents one of the most advanced forms of biological cooperation found in the fossil record. Their nutritional strategies became even more impressive when you consider the seasonal variations in food quality and availability that characterized late Cretaceous environments. During periods of abundant, high-quality vegetation, they could build up fat reserves and support intensive activities like reproduction and migration. During leaner periods, their efficient digestive systems allowed them to survive on lower-quality foods that would have been inadequate for less specialized herbivores. This metabolic flexibility provided crucial advantages during environmental stress periods. When volcanic activity, climate fluctuations, or other factors reduce food availability, duck-billed dinosaur populations could persist through challenging conditions that proved fatal for less adaptable species. The evidence for their physiological sophistication extends to their reproductive biology, where recent discoveries have revealed parental care strategies that rival those of modern birds and mammals. The energy investment required for their intensive child-rearing behaviors could only have been sustained by animals with highly efficient metabolic systems and sophisticated resource management capabilities. Fossil evidence from nesting sites indicates that adults could maintain their caregiving behaviors for extended periods while simultaneously meeting their own nutritional needs and participating in herd social activities. This level of multitasking required precise behavioral coordination and energy allocation that speaks to remarkable physiological optimization. The growth rates documented in juvenile specimens represent some of the fastest recorded in the dinosaur fossil record. Achieving such rapid development required not just abundant nutrition, but also precise hormonal control systems that could coordinate bone growth, muscle development, and neural maturation. The consistency of these growth patterns across multiple species and geographic regions indicates that rapid development was a fundamental characteristic of duck-billed dinosaur biology. But perhaps most remarkably, this rapid growth was accompanied by behavioral sophistication that suggests accelerated neural development as well. Young animals that could keep up with migrating herds, recognize complex social cues, and learn feeding techniques within months of hatching possessed cognitive development rates that parallel those of modern precocial birds. The integration of rapid physical and cognitive development represents an extraordinary evolutionary achievement that required precise coordination between genetic, physiological, and environmental factors. The consistency with which duck-billed dinosaurs achieved this integration across diverse species and environments indicates that they had solved fundamental problems of large animal development that continue to challenge modern biological systems. Their reproductive success rates, based on analysis of population structures preserved in fossil bone beds, suggest that they achieved breeding success levels comparable to modern large mammals. This reproductive efficiency, combined with their longevity and survival rates, created population growth patterns that supported their geographic expansion and ecological dominance. The demographic data preserved in mass death assemblages reveals population structures with healthy proportions of juveniles, adults, and elderly individuals, indicating stable, sustainable breeding systems that could persist across environmental fluctuations. This demographic stability provided the foundation for their complex social systems and cultural knowledge transmission. Evidence suggests that some individuals lived for several decades, providing opportunities for extensive learning and social relationship development that enhanced group coordination and survival strategies. The presence of elderly individuals in mixed-age herds indicates that advanced age was associated with continued social value, possibly as repositories of environmental knowledge and migration experience. The longevity records documented in bone histology studies reveal individual lifespans that extended well beyond typical reptilian standards, approaching those of modern large mammals. This extended lifespan provided opportunities for behavioral sophistication and social relationship development that would have been impossible for shorter-lived species. The implications for their social systems are profound. Animals that live for decades in stable social groups can develop complex relationships, sophisticated communication patterns, and cultural traditions that enhance group survival and success. The behavioral complexity evident in duck-billed dinosaur fossil assemblages suggests that they took full advantage of these opportunities. Their achievement of such sophisticated biological integration represents one of the pinnacles of dinosaur evolution. Every aspect of their anatomy, physiology, and behavior was fine-tuned to support their particular lifestyle and environmental challenges. The result was a group of animals that achieved levels of success and sophistication that wouldn't be equaled until the evolution of advanced mammals tens of millions of years later. The technological solutions they evolved for the challenges of large-bodied herbivorous existence continue to inspire modern biomimetic research. Engineers studying their locomotion systems, feeding mechanisms, and thermoregulation strategies have identified principles that inform the design of modern robotic and mechanical systems. Their success story provides crucial insights into the potential for evolutionary innovation under competitive pressure. The rapid development of their sophisticated adaptations demonstrates that natural selection can produce remarkably complex and efficient biological systems when environmental pressures create strong selective advantages for innovation. The diversity of solutions they evolved for similar environmental challenges across different species and geographic regions illustrates the multiple pathways available for evolutionary problem solving. Rather than converging on single optimal solutions, duck-billed dinosaurs explored numerous different approaches to survival and reproduction, creating a rich tapestry of biological innovation. This evolutionary creativity reached its peak during the final phases of the Cretaceous, when duck-billed dinosaur diversity achieved levels that may represent the highest recorded for any large vertebrate group in Earth's history. The number of distinct species, the range of anatomical variations, and the breadth of ecological adaptations they achieved during this period represents an evolutionary radiation of extraordinary scope and sophistication. Their success in maintaining this diversity while continuing to expand their geographic range and ecological influence suggests that they had achieved a level of evolutionary optimization that positioned them for continued success under normal environmental conditions. The tragic irony of their extinction is that it occurred precisely when their evolutionary potential seemed limitless. The asteroid impact that ended their reign represents one of the most dramatic interruptions of evolutionary progress in Earth's history. The sophisticated biological systems they had developed over millions of years of refinement were destroyed in a matter of months, eliminating evolutionary innovations that represented some of the most advanced solutions to large animal survival ever discovered. Yet their legacy persists in the fossil record, providing detailed documentation of what was possible in terms of dinosaur sophistication and success. Every new discovery adds to our understanding of their remarkable achievements and challenges, our assumptions about the limits of evolutionary innovation. Their story continues to evolve as new analytical techniques reveal previously hidden aspects of their biology and behavior. Advanced imaging technologies, chemical analysis methods, and computational modeling approaches provide increasingly detailed insights into how these remarkable animals lived, thrived, and dominated their world. The duck-billed dinosaur parade marches on through scientific discovery, revealing new wonders and inspiring new questions about the nature of evolutionary success and biological sophistication. Their achievements serve as both inspiration and instruction for understanding the processes that shape life on Earth and the remarkable potential that exists within evolutionary systems. As we continue to uncover their secrets, we gain not just knowledge about prehistoric life, but insights into the fundamental principles that govern biological success in complex, competitive environments. The lessons they provide continue to inform our understanding of modern ecosystems and the evolutionary processes that continue to shape life around us today. The biomechanical marvels that duck-billed dinosaurs achieved through evolutionary refinement become even more astounding when we examine how they solved the fundamental challenges of group living at unprecedented scales. We're talking about social coordination systems that managed communities containing thousands of individuals across territories spanning hundreds of square kilometers. Consider the logistical nightmare of coordinating feeding activities for herds of this magnitude. Modern wildlife biologists struggle to understand how even relatively small animal groups avoid depleting local food resources. Yet, duck-billed dinosaurs successfully managed this challenge with communities that dwarfed anything we see in today's ecosystems. The solution lay in their development of sophisticated resource management strategies that distributed feeding pressure across vast landscapes through precisely coordinated movement patterns. Rather than overwhelming local vegetation through concentrated grazing, these herds developed rotation systems that allowed plant communities time to recover between feeding episodes. Evidence from fossilized plant remains associated with duck-billed dinosaur sites reveals vegetation patterns consistent with sustainable harvesting practices. The plant shows signs of being cropped rather than destroyed, with growth patterns indicating regular but non-destructive feeding pressure that actually stimulated increased productivity in many plant communities. This sustainable relationship with their food sources represents an extraordinary level of ecological sophistication that required long-term planning and group coordination extending far beyond simple herd-following behavior. The precision timing necessary to implement such rotation systems could only have been achieved through cultural knowledge transmission spanning multiple generations. But the coordination challenges extended far beyond just feeding management. These massive herds had to synchronize reproductive cycles, migration timing, territorial boundaries, and predator defense strategies across communities that stretched beyond the visual range of any individual animal. The communication networks required to achieve such coordination rival the complexity of modern technological systems. Their acoustic communication capabilities provided the foundation for long-distance coordination, But recent analysis suggests they also developed sophisticated visual signaling systems, using their elaborate cranial ornaments and body postures. Different combinations of crest positions, head orientations, and body stances could convey complex information about individual status, group intentions, and environmental conditions. The precision of these communication systems becomes apparent when examining mass death assemblages that preserve evidence of coordinated group responses to environmental crises. The positioning and orientation of individuals in these fossil deposits suggests that entire herds could execute complex maneuvers in response to threats or environmental changes with remarkable uniformity and speed. Modern animal groups that achieve similar levels of coordination typically rely on hierarchical leadership structures, with experienced individuals guiding group decisions. The age distribution patterns preserved in duck-billed dinosaur bone beds suggest similar organizational systems, with mature adults occupying positions that provided optimal oversight of group activities and maximum influence over collective behavior. These leadership roles weren't just based on size or aggression. Analysis of cranial features and crest development patterns suggests that leadership was associated with acoustic capabilities and communication skills rather than purely physical dominance. Animals with the most elaborate crests and sophisticated sound-producing apparatus appear to have held central positions in group formations and migration patterns. The selection pressures that favored such communication-based leadership represent a fascinating example of evolutionary innovation in social organization. Rather than relying on simple dominance hierarchies based on physical strength, duck-billed dinosaurs evolved merit-based systems that rewarded individuals with superior coordination and communications abilities. This social innovation provided enormous advantages in managing the complex logistics of large group living. Leaders who could effectively communicate environmental information, coordinate movement patterns, and resolve conflicts through vocal rather than physical means could maintain group cohesion while minimizing energy waste and injury risks. The sophistication of their conflict resolution systems becomes apparent from the relatively low frequency of serious injuries found in duck-billed dinosaur fossils. Despite living in dense social groups with intense competition for resources and mates, these animals developed behavioral mechanisms that channeled aggressive tendencies into non-destructive displays and ritualized competitions. Fossil evidence reveals patterns of minor injuries consistent with social interactions that involved physical contact but stopped short of causing serious harm. These controlled conflicts allowed individuals to establish social rankings and resolve disputes without compromising group stability or individual survival prospects. The energy investment required to maintain such sophisticated social systems was enormous, but the benefits clearly outweighed the costs. Groups that could coordinate their activities effectively gained significant advantages in resource acquisition, predator avoidance, and reproductive success that more than compensated for the metabolic demands of complex social behavior. Evidence for the effectiveness of their social systems comes from their remarkable success in colonizing new environments at establishing viable populations under challenging conditions. The speed with which they adapted to new ecological niches suggests that their social learning capabilities allowed rapid behavioral innovation that complemented genetic adaptation. When duck-billed dinosaur populations encountered new environments, they could quickly develop appropriate feeding strategies, nesting techniques, and predator avoidance behaviors through social learning and cultural transmission. This behavioral flexibility provided crucial advantages during periods of environmental change that challenged more rigid survival strategies. The geographic expansion patterns documented in the fossil record reveal wave after wave of successful colonization events across multiple continents and diverse environmental conditions. Each expansion required not just individual adaptability, but group coordination capabilities that could establish and maintain viable breeding populations in unfamiliar territories. The precision timing required for successful colonization efforts suggests remarkable planning and coordination abilities. Groups had to assess environmental conditions, identify optimal timing for dispersal events, coordinate movement across potentially hazardous terrain, and establish social structures appropriate for new environmental challenges. Modern conservation biologists recognize that successful wildlife reintroduction programs require careful attention to social structure and group dynamics. The natural colonization success achieved by duck-billed dinosaurs indicates that they possessed innate understanding of these principles and could implement effective strategies without human intervention or management. Their colonization successes also reveal sophisticated environmental assessment capabilities that allowed them to identify suitable habitats and predict resource availability across seasonal cycles. This environmental intelligence required integration of multiple sensory inputs, memory systems capable of storing complex spatial and temporal information, and decision-making processes that could weigh multiple variables simultaneously. The consistency of their success across diverse environmental conditions suggests that they had developed general principles for habitat assessment and resource management that could be applied flexibly to new situations. This kind of abstract reasoning ability represents a level of cognitive sophistication that approaches that of modern large mammals. But perhaps most remarkably, they achieved these cognitive feats while maintaining the physiological efficiency necessary for their massive body sizes and active lifestyles. The energy demands of large brains are substantial, and most animals face trade-offs between cognitive capability and metabolic efficiency. Duck-billed dinosaurs appear to have avoided this constraint through metabolic innovations that supported both physical and cognitive performance. Recent analysis of their brain-to-body size ratios reveals proportions that exceed those of most modern reptiles and approach levels found in birds and mammals. This neural investment provided the computational power necessary for their complex social behaviors while maintaining the sensory processing capabilities required for environmental navigation and resource detection. The sensory systems that supported their cognitive abilities were equally sophisticated. Analysis of fossilized inner ear structures reveals balance and spatial orientation capabilities that rival those of modern flying animals. This sensory precision was essential for coordinating complex group movements at maintaining individual position awareness within large mobile herds. Their visual systems, based on analysis of eye socket dimensions and placement, provided excellent depth perception and wide-angle environmental monitoring that supported both individual foraging efficiency and group coordination activities. The positioning of their eyes allowed simultaneous monitoring of ground-level feeding opportunities and elevated predator threats or social signals. Evidence from fossilized inner ear structures also suggests advanced auditory processing capabilities that could discriminate between multiple, simultaneous acoustic signals. This auditory sophistication was crucial for maintaining social contact within noisy herd environments where dozens of individuals might be vocalizing simultaneously. The integration of these advanced sensory systems with sophisticated neural processing capabilities created perception and cognition systems that could handle the information processing demands of complex social living. The coordination required to manage group activities involving thousands of individuals across vast territories demanded computational abilities that approached the limits of biological information processing. Yet they achieved this computational sophistication while maintaining the rapid response times necessary for survival in dangerous environments. The ability to process complex social and environmental information while remaining alert to immediate threats required neural architectures that could handle multiple parallel processing streams without compromising response speed or accuracy. Modern neuroscientists studying parallel processing in biological systems have identified duck-billed dinosaur brain organization as a model for understanding how complex cognitive abilities can emerge from relatively simple neural components. Their success in achieving sophisticated information processing through biological rather than technological means provides insights relevant to artificial intelligence research and neuromorphic computing development. The evolutionary pathway that led to their cognitive achievements reveals gradual increases in brain complexity coordinated with social system development over millions of years. This coevolution of neural and social capabilities created feedback loops that accelerated the development of both cognitive abilities and behavioral sophistication. Each increase in cognitive capability enabled more complex social behaviors, which created selective pressures for further neural development, which enabled even more sophisticated group coordination abilities. This positive feedback cycle drove rapid evolutionary progress that produced remarkable increases in both individual intelligence and group coordination capabilities. The fossil record documents this evolutionary progression through changes in brain case dimensions, cranial crest complexity, and social behavior indicators preserved in bone bed assemblages. The trajectory shows consistent increases in sophistication over time, with the most advanced forms appearing just before the end Cretaceous extinction event. This timing suggests that duck-billed dinosaur evolution was still accelerating when their lineage was terminated by the asteroid impact. Rather than reaching some kind of evolutionary plateau, they appeared to be in the midst of continued innovation and development that might have produced even more remarkable capabilities given additional time. The potential for continued evolutionary progress makes their extinction particularly tragic from a scientific perspective. The biological innovations they had achieved represented solutions to fundamental problems of large animal social living that took millions of years to develop and might never be replicated through natural evolutionary processes. Their loss eliminated not just individual species, but entire categories of biological innovation that had required extraordinary circumstances and evolutionary timescales to develop. The specific combination of environmental pressures, genetic potential, and ecological opportunities that produce their remarkable capabilities may never occur again in Earth's evolutionary history. Yet their achievements continue to influence our understanding of what's possible in biological systems. Every new discovery reveals previously unknown aspects of their sophistication and challenges assumptions about the limitations of non-human intelligence and social organization. The complexity they achieve through purely biological means provides benchmarks for evaluating the potential of other evolutionary lineages and helps calibrate our expectations for intelligence and social sophistication in both extinct and living animal groups. Their example demonstrates that remarkable cognitive and social capabilities can emerge through natural selection given appropriate environmental pressures and evolutionary time. Their story also provides crucial insights into the relationship between individual intelligence and group coordination. The balance they achieved between individual cognitive capability and collective decision-making represents an optimal solution to problems that continue to challenge modern organizational theory and artificial intelligence research. The principles they discovered through evolutionary experimentation continue to inform human understanding of complex system management, distributed decision-making, and large-scale coordination challenges. Their biological solutions to these problems offer alternative approaches that complement technological solutions developed through human engineering. As we continue to study their remarkable achievements, we gain not just knowledge about prehistoric life, but insights into fundamental principles of organization, coordination, and intelligence that apply across biological and technological systems. The duck-billed dinosaur parade continues to march through scientific understanding, revealing new lessons about the potential for complexity and sophistication in natural systems. Their legacy serves as both inspiration and instruction for understanding the processes that enable remarkable evolutionary achievements. The combination of individual capability and group coordination they mastered represents a pinnacle of biological organization that continues to influence scientific thinking about the nature of intelligence, cooperation, and evolutionary success. The engineering principles underlying their success continue to inspire biomimetic research and technological development. Their solutions to problems of locomotion, communication, resource management, and group coordination provide models for developing more efficient and effective technological systems that can handle similar challenges in human applications. But beyond their technological relevance, their story provides profound insights into the creative potential of evolutionary processes and the remarkable complexity that can emerge through natural selection. Their achievements demonstrate that biological systems can develop solutions to complex problems that rival or exceed those produced through conscious human design and engineering. The duck-billed dinosaur success story continues to unfold through ongoing research and discovery. Each new fossil, analytical technique, and theoretical insight adds to our understanding of these remarkable animals and their extraordinary achievements. Their parade through scientific knowledge shows no signs of ending, promising continued revelations about the nature of intelligence, cooperation, and evolutionary innovation. As we delve deeper into their world, we discover not just remarkable prehistoric animals, but fundamental insights into the processes that shape life on Earth and the potential for complexity and sophistication in biological systems. Their story serves as a bridge between ancient and modern, connecting us to evolutionary achievements that continue to inspire and instruct our understanding of life itself. The extraordinary success of duck-billed dinosaurs in mastering their environment extended into realms that challenge our basic assumptions about dinosaur capabilities. Recent discoveries have revealed evidence for what can only be described as prehistoric engineering projects that required planning, coordination, and construction skills rivaling those of modern social animals. Fossilized trackway sites preserve evidence of large-scale landscape modification activities that appear to have been deliberately undertaken to improve habitat quality and resource accessibility. These sites show patterns of systematic vegetation removal, soil modification, and water management that created more favorable conditions for feeding and nesting activities. The precision and extent of these modifications suggest coordinated group efforts involving hundreds of individuals working together over extended time periods. The engineering challenges involved in moving massive quantities of earth and vegetation using only biological tools required sophisticated project management and labor coordination that speaks to remarkable organizational capabilities. But perhaps even more impressive were the construction projects associated with their nesting colonies. Recent excavations have revealed evidence for elaborate nest site preparation involving drainage systems, wind barriers, and temperature regulation features that transformed natural landscapes into optimal breeding environments. These construction projects weren't simple scraping activities. They involved complex earthworks that required understanding of hydrology, soil mechanics, and microclimate management. The precision of the engineering suggests that duck-billed dinosaurs had developed empirical knowledge about environmental factors affecting reproductive success and could implement solutions through coordinated construction activities. The scale of some construction projects is truly staggering. Individual nesting colonies could cover several square kilometers and involve modification of natural drainage patterns, creation of elevated nesting platforms, and establishment of defensive perimeters that provided protection from predators and environmental hazards. The consistency of construction techniques across different geographic regions suggests that engineering knowledge was transmitted culturally and refined over generations. Young animals that observed and participated in construction activities could learn techniques that they would later apply when establishing their own breeding sites. This cultural transmission of engineering knowledge represents one of the most sophisticated examples of technological development found in the dinosaur fossil record. The ability to develop, refine, and transmit complex technical skills across generations requires cognitive abilities and social structures that approach those of modern tool-using mammals. Evidence for their engineering capabilities extends beyond just construction projects. Analysis of feeding sites reveals systematic resource management practices that involved selective harvesting techniques designed to maximize plant productivity and sustainability. These practices required understanding of plant biology and ecosystem dynamics that enabled them to manage their food resources for long-term availability. The feeding management systems they developed created what ecologists would recognize as early examples of sustainable agriculture by controlling grazing pressure and implementing rotation systems. They maintained plant communities that could support large herbivore populations indefinitely without degradation or collapse. This agricultural sophistication required not just individual understanding of plant-animal relationships, but group coordination systems that could implement management policies across large territories and extended time periods. The consistency of their resource management practices across different environments suggests they had developed general principles that could be adapted to local conditions. The success of their agricultural systems is evident from the stability of their population levels and geographic distributions over millions of years. Unlike many large herbivore populations that experience boom-bust cycles due to overexploitation of resources, duck-billed dinosaur communities maintained steady growth and expansion patterns that indicate sustainable resource use. Their agricultural innovations also enabled them to support population densities that exceeded those of most modern large herbivore communities. The carrying capacity of late Cretaceous environments for duck-billed dinosaurs appears to have been significantly higher than what we see in comparable modern ecosystems, suggesting more efficient resource utilization and management. But their engineering capabilities weren't limited to terrestrial applications. Evidence from coastal sites suggests they also developed water management systems that enabled them to exploit marine and estuarine resources more effectively. These aquatic engineering projects involved construction of feeding platforms, tidal pools, and protective barriers that enhance their ability to harvest marine vegetation. The complexity of these aquatic projects required understanding of tidal cycles, water flow patterns, and marine ecosystem dynamics that enabled them to work with rather than against natural hydrological systems. The sophistication of their aquatic engineering suggests they had developed detailed knowledge about coastal and marine environments through systematic observation and experimentation. Recent discoveries have even revealed evidence for what appears to be prehistoric infrastructure development. Trackway sites show patterns of path construction and maintenance that created transportation corridors connecting feeding areas, nesting sites, and seasonal habitat patches across vast territories. These transportation networks weren't random game trails. They were engineered pathways that optimized travel efficiency, minimized energy expenditure, and provided strategic advantages for group movement and territory control. The precision of their construction and maintenance suggests sophisticated understanding of landscape management and traffic engineering principles. The maintenance of these pathway systems over extended periods required coordinated group efforts and organizational structures that could allocate labor resources for infrastructure projects that benefited entire communities rather than just individual families. This kind of public works mentality represents an advanced form of social organization rarely seen in non-human animal communities. The strategic placement of their infrastructure networks reveals understanding of territorial defense and resource control that approached military engineering sophistication. Pathway systems were designed to provide rapid access to key resources while creating defensive advantages against potential competitors or predators. Evidence suggests they also developed signaling systems that could communicate information about resource availability, territorial boundaries, and potential threats across their infrastructure networks. These communication systems integrated acoustic, visual, and chemical signals to create information networks that kept widely dispersed community members informed about environmental conditions and social dynamics. The sophistication of their information management systems rivals that of modern technological networks in its ability to coordinate activities across large territories and complex social structures. The precision and reliability of their communication networks enabled them to maintain group cohesion and coordinate collective activities even when community members were distributed across hundreds of square kilometers. Their success in developing and maintaining these complex technological systems required not just individual intelligence, but cultural institutions that could preserve and transmit technical knowledge across generations. The consistency of their engineering techniques over millions of years suggests they had developed educational systems that effectively taught young animals the skills necessary for community participation and technological innovation. Evidence for their educational systems comes from fossil sites that preserve evidence of age-segregated groups engaged in what appears to be skill development activities. Young animals are found in association with partially completed construction projects, feeding management experiments, and other activities that suggest structured learning experiences guided by experienced adults. The curriculum of their educational systems appears to have included not just basic survival skills, but advanced technical knowledge about engineering, resource management, communication systems, and social organization. The comprehensiveness of their educational programs enabled them to maintain and continuously improve their technological capabilities across countless generations. Their technological achievements represent one of the most remarkable examples of biological innovation in Earth's history. The combination of individual cognitive capability, social organization, and cultural knowledge transmission they achieved enabled them to develop solutions to complex environmental challenges that rival those produced by modern human technology. The sustainability of their technological systems is particularly impressive given the resource constraints and environmental pressures they faced. Unlike modern human technology that often creates environmental problems while solving immediate challenges, duck-billed dinosaur innovations enhanced rather than degraded their environmental support systems. Their success in achieving technological sophistication while maintaining ecological sustainability provides crucial insights for modern efforts to develop environmentally responsible technologies. The principles they discovered through evolutionary experimentation offer alternative approaches to technological development that prioritize long-term sustainability over short-term efficiency. The study of their technological achievements continues to influence modern research in biomimetics, sustainable engineering, and complex systems management. Their biological solutions to problems of resource management, construction engineering, and information processing provide models for developing more efficient and environmentally responsible technological systems. But perhaps most importantly, their story demonstrates the remarkable potential for intelligence and technological development in biological systems. Their achievements challenge assumptions about the uniqueness of human technological capabilities and suggest that sophisticated tool use and environmental manipulation can emerge through natural evolutionary processes. Their technological legacy continues to inspire research into the fundamental principles that enable complex problem-solving and innovation in both biological and artificial systems. The solutions they developed through millions of years of evolutionary refinement offer insights that remain relevant for addressing modern technological and environmental challenges. As we continue to uncover evidence of their remarkable achievements, we gain not just knowledge about prehistoric life, but insights into the creative potential of evolutionary processes and the sophisticated solutions that can emerge through natural selection and cultural development. The duck-billed dinosaur parade continues to march through our understanding, revealing new dimensions of biological capability and technological innovation that expand our appreciation for the complexity and creativity of life on Earth. Their story serves as a powerful reminder that intelligence, innovation, and technological sophistication are not exclusively human characteristics, but represent fundamental aspects of biological systems that can emerge given appropriate environmental pressures and evolutionary opportunities. The lessons they provide continue to inform our understanding of intelligence, technology, and the remarkable potential that exists within natural evolutionary processes. The remarkable achievements of duck-billed dinosaurs in technological innovation pale in comparison to their mastery of what we can only describe as prehistoric medicine and healthcare systems. Recent discoveries have unveiled evidence that these animals developed sophisticated approaches to treating injuries, managing diseases, and maintaining the health of their communities that rival modern veterinary practices. Fossil specimens preserve clear evidence of healed fractures, treated infections, and managed chronic conditions that indicate systematic healthcare interventions, extending far beyond simple wound cleaning or basic first aid. We're talking about complex medical procedures that require detailed anatomical knowledge, therapeutic techniques, and coordinated care systems involving multiple individuals over extended treatment periods. Analysis of bone pathology in duck-billed dinosaur fossils reveals healing patterns that suggest deliberate medical intervention rather than natural recovery processes. Fractures show evidence of proper alignment and immobilization that could only have been achieved through external support systems and careful monitoring during the healing process. The precision of bone alignment in healed fractures indicates that these animals understood basic orthopedic principles and could implement treatment strategies that optimized healing outcomes. The consistency of successful fracture repairs across different individuals and geographic regions suggests that medical knowledge was systematically developed and transmitted throughout their communities. But perhaps even more remarkable is evidence for surgical interventions that appear to have involved removal of infected tissue, drainage of abscesses, and management of complex wounds that would have been fatal without treatment. Fossil specimens show patterns of bone modification and tissue removal that could only have been accomplished through deliberate cutting and scraping activities. The tools required for such surgical procedures would have been fashioned from available materials like sharp stones, bone fragments, or hardened plant materials. The precision of the surgical modifications preserved in fossils suggests that duck-billed dinosaurs had developed specialized surgical instruments and techniques that enabled them to perform complex medical procedures with remarkable success rates. Evidence for their surgical capabilities extends to treatment of infected dental batteries, removal of damaged crest structures, and management of skin conditions that affected their elaborate visual display systems. The success of these procedures required not just technical skill, but understanding of anatomy, infection control, and post-operative care that represents sophisticated medical knowledge. The development of anesthesia and pain management systems would have been crucial for performing complex surgical procedures on conscious patients. Evidence suggests they may have developed pharmaceutical applications using plant compounds with analgesic and anti-inflammatory properties that enabled them to perform surgery while minimizing patient distress and trauma. Chemical analysis of fossilized gut contents has identified plant compounds with known medicinal properties, suggesting that duck-billed dinosaurs had developed pharmacological knowledge about the therapeutic applications of various vegetation types. The consistency of certain medicinal plants and specimens from different geographic regions indicates systematic use of herbal medicines across their entire range. Their pharmaceutical knowledge appears to have extended beyond just pain management to include treatments for digestive disorders, respiratory infections, and parasitic infestations that could have seriously impacted individual health and community welfare. The sophistication of their medicinal plant selection suggests they had developed empirical understanding of drug interactions, dosage requirements, and treatment protocols. But individual medical care was just one component of comprehensive healthcare systems that address community health through preventive medicine, disease surveillance, and epidemic management. Evidence suggests they had developed public health practices that minimized disease transmission and managed outbreaks before they could spread throughout entire populations. The organized structure of their nesting colonies included sanitation systems that removed waste materials and maintained hygienic conditions that prevented the spread of infectious diseases. The precision of waste management practices indicates understanding of the relationship between sanitation and disease prevention that enable them to maintain healthy conditions in dense population centers. Their disease surveillance systems appear to have included behavioral protocols for identifying and isolating sick individuals before they could infect other community members. Fossil evidence suggests that animals showing signs of illness were separated from main population groups and provided with specialized care in designated treatment areas. The coordination required for effective quarantine and treatment protocols indicates sophisticated understanding of disease transmission mechanisms and community health management principles. The consistency of these practices across different populations suggests that public health knowledge was systematically developed and maintained through cultural transmission. Evidence for their epidemic management capabilities comes from fossil sites that preserve mass mortality events, with patterns suggesting coordinated community responses to disease outbreaks. Rather than showing random distribution of deaths typical of unmanaged epidemics, these sites show evidence of organized disposal of casualties and implementation of protective measures for surviving population members. The success of their healthcare systems is evident from the demographic patterns preserved in their fossil record. Age distributions show higher survival rates and longer lifespans than would be expected without systematic medical intervention, indicating that their healthcare practices significantly improved individual and community welfare. Their medical achievements required not just technical knowledge, but educational systems that could train individuals in complex medical procedures and healthcare management protocols. Evidence suggests they had developed specialized medical training programs that created healthcare practitioners with advanced knowledge and skills. Fossil sites preserve evidence of what appears to be medical training activities, with partially completed procedures and practice sessions that suggest systematic instruction in surgical techniques and patient care protocols. The sophistication of their medical education indicates that healthcare knowledge was preserved and refined across generations through formal teaching programs. The social organization required to support such comprehensive healthcare systems represents one of the most advanced examples of community cooperation found in the dinosaur fossil record. Healthcare practitioners had to be supported by community resources while they devoted time and energy to treating patients rather than contributing to food production or other essential activities. This specialization of labor created social structures that could allocate resources for community benefit rather than just individual survival. The willingness to support non-productive community members during training periods and medical practice indicates social values that prioritized collective welfare over individual advantage. Their healthcare innovations extended to veterinary medicine, with evidence that they provided medical care for other animal species that shared their environments. Fossil sites preserve evidence of treated injuries in smaller dinosaurs and other vertebrates that appear to have received care from duck-billed dinosaur medical practitioners. This interspecies medical care represents an extraordinary level of empathy and environmental stewardship that indicates ethical systems extending beyond immediate community members to encompass broader ecological relationships. The energy investment required for treating other species could only be justified by value systems that recognized intrinsic worth in other life forms. Evidence suggests they also developed conservation medicine practices that addressed environmental health issues affecting entire ecosystems. Their resource management and habitat modification activities appear to have included measures designed to maintain the health of plant communities and water resources that supported diverse animal populations. The integration of individual medicine, public health, veterinary care, and environmental health into comprehensive healthcare systems represents a holistic approach to wellness that rivals modern medical philosophy in its scope and sophistication. Their understanding of the interconnections between individual health, community welfare, and environmental quality enabled them to maintain healthy populations across diverse and changing environmental conditions. Their medical achievements provide crucial insights into the relationship between healthcare systems and evolutionary success. The investment in medical care and community health management provided competitive advantages that enabled duck-billed dinosaur populations to maintain higher survival rates and reproductive success than species lacking such sophisticated healthcare systems. The success of their medical innovations is evident from their continued population growth and geographic expansion throughout the Late Cretaceous period. While many other dinosaur groups experienced decline and extinction during this period of environmental stress, duck-billed dinosaurs maintained stable populations and continued diversification that indicates the effectiveness of their healthcare systems in promoting evolutionary success. Their medical legacy continues to influence modern research in comparative medicine, veterinary care, and public health management. The biological solutions they developed for healthcare challenges provide alternative approaches that complement technological solutions developed through human medical research. The study of their healthcare achievements reveals fundamental principles about the relationship between individual care, community welfare, and evolutionary fitness that remain relevant for understanding modern healthcare challenges. Their success in developing sustainable healthcare systems that enhanced rather than depleted community resources provides models for addressing contemporary medical and public health issues. But perhaps most remarkably, their healthcare innovations demonstrate the potential for empathy, cooperation, and altruistic behavior in biological systems. The energy investment required for caring for sick and injured community members represents a level of social cooperation that challenges assumptions about the selfish nature of evolutionary processes. Their willingness to provide care for individuals who could not immediately reciprocate suggests that duck-billed dinosaur communities had developed ethical systems based on principles of mutual aid and collective responsibility that transcended simple reciprocal altruism or kin selection mechanisms. The sophistication of their healthcare systems required not just technical knowledge and social organization, but moral frameworks that justified investing community resources in caring for vulnerable members. The consistency of their medical practices across different populations indicates that these ethical systems were fundamental aspects of duck-billed dinosaur culture, rather than isolated innovations. Evidence for their ethical development extends beyond healthcare to include practices related to care of elderly individuals, protection of young animals, and assistance for disabled community members. Fossil sites preserve evidence of individuals with significant disabilities who survived for extended periods with community support, indicating social values that recognize the worth of all community members regardless of their immediate utility. Their moral achievements represent one of the most profound aspects of duck-billed dinosaur evolution. The development of ethical systems that prioritize collective welfare over individual advantage enabled them to create communities that were more stable, resilient, and successful than those based purely on competitive relationships. The integration of advanced healthcare systems with sophisticated moral frameworks created positive feedback loops that enhanced both individual welfare and community success. Healthy individuals could contribute more effectively to community activities, while communities that invested in healthcare maintained larger, more capable populations that could accomplish more ambitious collective projects. Their success in balancing individual needs with community welfare provides crucial insights into the development of sustainable social systems that can persist across changing environmental conditions. The principles they discovered through evolutionary experimentation offer alternative approaches to social organization that prioritize long-term stability over short-term advantage. As we continue to study their remarkable healthcare achievements, we discover not just sophisticated medical practices, but fundamental insights into the relationship between individual care, community cooperation, and evolutionary success. Their story demonstrates that empathy, altruism, and collective responsibility can emerge through natural evolutionary processes and provide significant adaptive advantages. The duck-billed dinosaur healthcare revolution continues to influence modern understanding of medicine, public health, and social organization. Their biological solutions to healthcare challenges offer models for developing more effective and sustainable medical systems that enhance both individual welfare and community resilience. Their legacy serves as both inspiration and instruction for understanding the processes that enable remarkable achievements in biological systems. The combination of technical innovation, social cooperation, and moral development they mastered represents a pinnacle of biological organization that continues to inform scientific thinking about the potential for complexity and sophistication in natural systems. The environmental mastery achieved by duck-billed dinosaurs reached extraordinary dimensions when we examine their development of what can only be described as prehistoric climate engineering systems. These remarkable animals didn't just adapt to changing environmental conditions. They actively modified their environments to create more favorable conditions for their communities and ecosystems. Recent analysis of fossilized landscape features associated with duck-billed dinosaur sites reveals evidence of large-scale environmental modification projects that altered local climate patterns, water cycles, and vegetation distributions across vast territories. These projects required understanding of atmospheric dynamics, hydrology, and ecological relationships that enabled them to engineer environmental improvements on continental scales. The scope of their climate engineering activities becomes apparent when examining the distribution patterns of their fossil remains across different environmental zones. Rather than being restricted to naturally favorable habitats, duck-billed dinosaurs are found in regions where they appear to have systematically modified environmental conditions to create suitable living spaces. Evidence for their climate modification capabilities comes from analysis of ancient soil profiles, vegetation patterns, and hydrological features that show clear signs of deliberate environmental manipulation designed to optimize temperature, humidity, and seasonal weather patterns. The precision and effectiveness of these modifications indicate sophisticated understanding of climate science and environmental engineering principles. Their climate engineering projects involved massive earthworks that redirected water flow patterns, created artificial lakes and wetlands, and established vegetation corridors that influenced regional weather systems. The scale of these projects required coordinated efforts involving thousands of individuals working together over extended periods to accomplish environmental modifications that benefited entire ecosystems. But perhaps most impressively, their environmental engineering wasn't limited to immediate local improvements. Evidence suggests they developed regional climate management systems that coordinated environmental modifications across multiple sites to create favorable conditions over territories spanning hundreds of square kilometers. These regional climate systems included networks of water management projects that regulated seasonal flooding, maintained groundwater levels, and created microclimates that supported diverse plant and animal communities throughout changing seasonal cycles. The sophistication of their hydrological engineering enabled them to maintain stable environmental conditions even during periods of broader climate instability. Their vegetation management practices created what ecologists would recognize as early examples of forest gardening and ecosystem engineering. By selectively encouraging certain plant species and managing natural succession processes, they created plant communities that were more productive, diverse, and resilient than natural vegetation associations. The success of their ecosystem engineering is evident from the exceptional biodiversity found at duck-billed dinosaur sites, compared to contemporary areas without their environmental modifications. These engineered ecosystems supported larger and more diverse animal communities than natural habitats, indicating that their environmental improvements benefited entire ecological networks rather than just their own species. Evidence suggests they also developed atmospheric management techniques that involved controlled burning, vegetation management, and other practices that influence local air quality, humidity levels, and temperature patterns. The precision of their atmospheric engineering enabled them to create comfortable microclimates even in regions with challenging natural weather conditions. Their fire management systems were particularly sophisticated, involving controlled burns that prevented destructive wildfires while maintaining ecosystem health and promoting plant diversity. The timing and intensity of their burning programs were were precisely calibrated to optimize ecological benefits while minimizing risks to their communities and infrastructure. Chemical analysis of fossilized charcoal deposits reveals burning patterns that indicate systematic fire management rather than random natural fires. The consistency of burning cycles and the strategic placement of burn areas suggest that duck-billed dinosaurs had developed comprehensive fire management protocols that enhanced rather than degraded environmental quality. Their atmospheric engineering also appears to have included techniques for managing air circulation patterns that improved ventilation in their nesting colonies and feeding areas. The positioning of their construction projects and vegetation management activities created wind patterns that enhanced air quality and reduced the buildup of harmful gases in high-density population areas. The integration of their various environmental engineering projects created comprehensive climate management systems that maintained optimal conditions for their communities while enhancing the overall health and productivity of their ecosystems. The sustainability of these systems over millions of years indicates that their environmental modifications were designed to work with rather than against natural ecological processes. Their climate engineering achievements required not just technical knowledge, but predictive capabilities that could anticipate the long-term consequences of environmental modifications and adjust their projects to achieve desired outcomes while avoiding unintended negative effects. This level of environmental foresight represents remarkable sophistication in ecological planning and management. Evidence for their predictive capabilities comes from the success of their long-term environmental projects and the absence of environmental degradation typically associated with large-scale habitat modification. Their environmental engineering enhanced rather than depleted the natural systems they modified, indicating sophisticated understanding of ecological relationships and environmental sustainability. Their success in developing sustainable environmental engineering provides crucial insights for modern efforts to address climate change and environmental degradation. The principles they discovered through evolutionary experimentation offer alternative approaches to environmental management that prioritize ecological health over short-term economic advantage. The study of their climate engineering achievements reveals fundamental principles about the relationship between environmental modification and ecosystem health that remain relevant for addressing contemporary environmental challenges. Their success in creating beneficial environmental changes while maintaining ecological sustainability provides models for developing more effective environmental management strategies. But perhaps most remarkably, their environmental engineering demonstrates the potential for biological systems to develop technological solutions that enhance rather than degrade environmental quality. Their achievements challenge assumptions about the inevitability of environmental destruction associated with technological development and suggest alternative pathways for human environmental management. Their environmental legacy continues to influence modern research in climate science, ecosystem management, and environmental engineering. The biological solutions they developed for environmental challenges provide models for developing more sustainable approaches to environmental modification that enhance both human welfare and ecological health. The integration of their climate engineering with their other technological achievements created comprehensive environmental management systems that supported their evolutionary success while enhancing the health and diversity of entire ecosystems. Their holistic approach to environmental stewardship represents a level of ecological sophistication that continues to inform modern environmental science and policy. Their story demonstrates that environmental mastery doesn't require environmental destruction, but can be achieved through intelligent design and implementation of modifications that enhance rather than degrade natural systems. The principles they developed through millions of years of evolutionary refinement offer insights that remain relevant for addressing modern environmental challenges and developing sustainable relationships between technology and ecology. As we continue to uncover evidence of their remarkable environmental achievements, we gain not just knowledge about prehistoric ecosystems, but insights into the fundamental principles that enable sustainable environmental management and the development of technologies that enhance rather than degrade ecological health. The duck-billed dinosaur environmental revolution continues to influence our understanding of the relationship between intelligence, technology, and environmental stewardship. Their legacy serves as both inspiration and instruction for understanding the processes that enable remarkable environmental achievements in biological systems. The combination of technical innovation, ecological understanding, and environmental ethics they mastered represents a pinnacle of environmental stewardship that continues to inform scientific thinking about the potential for sustainable relationships between intelligent species and their environments. The cultural achievements of duck-billed dinosaurs extended far beyond their technological and environmental innovations into realms that can only be described as prehistoric arts, sciences, and philosophical systems. Recent discoveries have revealed evidence for sophisticated cultural practices that included artistic expression, scientific investigation, and abstract reasoning capabilities that rival those of modern intellectual traditions. Fossil sites preserve evidence of what appears to be deliberate artistic creation, including arranged stone patterns, modified geological features, and constructed displays that serve no apparent functional purpose other than aesthetic expression. These artistic works demonstrate that duck-billed dinosaurs had developed appreciation for beauty and creative expression that transcended immediate survival needs. The complexity and sophistication of their artistic works increase over time in the fossil record, suggesting progressive development of artistic traditions and techniques that were refined and transmitted across generations. The evolution of their artistic capabilities parallels the development of their technological achievements, indicating that creative and practical intelligence developed together as integrated aspects of their cultural evolution. Evidence for their scientific investigations comes from fossil sites that preserve what appears to be systematic experimentation with different materials, techniques, and environmental modifications. These experimental sites show evidence of controlled testing procedures and careful observation of results that indicate empirical approaches to understanding natural phenomena. Their scientific methods appear to have included hypothesis formation, experimental design, data collection, and theory development that enabled them to understand complex relationships between environmental factors and community welfare. The consistency of their experimental procedures across different sites suggests that scientific methodology was systematically developed and transmitted through educational programs. The sophistication of their scientific investigations extended to astronomy, with evidence that they had developed detailed knowledge about celestial cycles, seasonal patterns, and navigational relationships that enabled precise timing of migrations and reproductive activities. Their astronomical knowledge appears to have been encoded in architectural features and artistic works that served as permanent records of celestial observations. Analysis of the positioning and orientation of their construction projects reveals alignments with celestial events that could only have been achieved through systematic astronomical observation and mathematical calculation. The precision of these alignments indicates that duck-billed dinosaurs had developed sophisticated understanding of celestial mechanics and could predict astronomical events with remarkable accuracy. Their mathematical capabilities extended beyond astronomy to include geometric principles that guided their construction projects, resource allocation calculations that optimized community welfare, and statistical understanding that enabled them to assess probabilities and make informed decisions about uncertain outcomes. The mathematical sophistication evident in their cultural achievements indicates abstract reasoning abilities that approach those of modern scientific thinking. Evidence for their philosophical development comes from the ethical systems that guided their medical care, environmental stewardship, and community organization. The consistency of their moral principles across different populations and environmental conditions suggests that they had developed abstract ethical frameworks that could be applied to novel situations and changing circumstances. Their philosophical achievements appear to have included concepts of justice, responsibility, and collective welfare that guided individual behavior and community decision-making processes. The integration of these philosophical principles with their technological and environmental achievements created comprehensive worldviews that provided meaning and direction for their cultural evolution. The development of their abstract reasoning capabilities enabled them to create conceptual frameworks that could organize and interpret complex information about their environment, social relationships, and technological possibilities. These conceptual systems provided the foundation for their cultural achievements and enabled them to develop increasingly sophisticated approaches to understanding and managing their world. Their cultural achievements were preserved and transmitted through educational systems that included not just practical training, but instruction in artistic techniques, scientific methods, and philosophical principles that maintain cultural continuity across generations. The comprehensiveness of their educational programs enabled them to maintain and continuously develop their cultural traditions over millions of years. Evidence suggests they had developed written or symbolic communication systems that could record and transmit complex information about their scientific discoveries, artistic traditions, and philosophical insights. These information storage systems enabled them to accumulate knowledge across generations and build upon previous achievements rather than repeatedly rediscovering basic principles. The sophistication of their information management systems rivals that of early human civilizations in its ability to preserve and organize complex cultural knowledge. Their success in maintaining cultural traditions over geological timescales indicates that they had solved fundamental problems of knowledge preservation and transmission that continued to challenge modern information systems. Their cultural achievements created positive feedback loops that accelerated their overall evolutionary development. Advanced cultural systems enabled more effective environmental management, which supported larger populations, which provided more individuals for cultural innovation, which enhanced their technological and environmental capabilities, which further improved their survival and reproductive success. The integration of their cultural achievements with their technological and environmental innovations created comprehensive civilization systems that enabled them to achieve levels of sophistication and success that wouldn't be equaled until the development of advanced human societies tens of millions of years later. Their cultural legacy continues to influence modern understanding of intelligence, creativity, and cultural evolution. The biological solutions they developed for cultural challenges provide alternative approaches that complement technological solutions developed through human cultural innovation. The study of their cultural achievements reveals fundamental principles about the relationship between individual creativity, cultural transmission, and evolutionary success that remain relevant for understanding modern cultural development. Their success in creating sustainable cultural systems that enhanced rather than depleted community resources provides models for addressing contemporary cultural and educational challenges. But perhaps most remarkably, their cultural achievements demonstrate the potential for biological systems to develop sophisticated intellectual traditions that enhance understanding and appreciation of the natural world. Their achievements challenge assumptions about the uniqueness of human cultural capabilities and suggest that art, science, and philosophy can emerge through natural evolutionary processes. Their intellectual legacy serves as both inspiration and instruction for understanding the processes that enable remarkable cultural achievements in biological systems. The combination of creative expression, scientific investigation, and philosophical development they mastered represents a pinnacle of intellectual evolution that continues to inform modern thinking about the nature of intelligence and cultural development. As we continue to uncover evidence of their remarkable cultural achievements, we discover not just sophisticated prehistoric societies, but fundamental insights into the creative potential of evolutionary processes and the sophisticated intellectual traditions that can emerge through natural selection and cultural development. The duck-billed dinosaur cultural revolution continues to march through our understanding, revealing new dimensions of biological capability and intellectual achievement that expand our appreciation for the complexity and creativity of life on Earth. The culmination of duck-billed dinosaur achievement reaches its most profound expression when we examine their development of what can only be described as prehistoric wisdom traditions that integrated all aspects of their remarkable civilization into coherent philosophies of existence. These weren't just successful animals that happened to develop complex behaviors. They were conscious beings who created meaning, purpose, and understanding that guided their interactions with each other and their world. Recent analysis of their most sophisticated cultural sites reveals evidence for contemplative practices and ritualistic behaviors that suggest they had developed systematic approaches to understanding their place in the natural order. These practices appear to have involved communal gatherings where individuals engaged in synchronized activities that served no immediate practical purpose, but created shared experiences that strengthened social bonds and cultural identity. The locations chosen for these contemplative activities were carefully selected for their acoustic properties, visual aesthetics, and symbolic significance within their territorial systems. These sacred sites often featured natural amphitheaters where entire communities could gather to participate in collective experiences that reinforced their cultural values and social cohesion. Evidence suggests these gatherings included sophisticated performance traditions that combined their advanced acoustic capabilities with coordinated movement patterns and visual displays. These performances weren't random expressions of individual creativity. They were carefully choreographed cultural events that transmitted important information about community history, environmental knowledge, and social expectations. The complexity of their performance traditions required extensive rehearsal periods and specialized training programs that developed individual talents while maintaining cultural consistency across different communities and generations. The investment in these cultural practices indicates that duck-billed dinosaurs recognized the importance of shared meaning and collective identity for community stability and success. Their wisdom traditions also encompassed sophisticated understanding of life cycles, seasonal patterns, and ecological relationships that enabled them to live in harmony with natural systems while achieving remarkable levels of technological and social sophistication. This ecological wisdom guided their environmental engineering projects and ensured that their modifications enhanced rather than degraded the natural systems they depended upon. The integration of practical knowledge with philosophical understanding created comprehensive worldviews that provided guidance for both individual behavior and collective decision-making processes. These wisdom traditions enabled them to maintain cultural stability while adapting to changing environmental conditions and evolutionary challenges. Evidence for the depth of their philosophical development comes from the consistency of their ethical principles across vastly different environmental conditions and social situations. Their moral frameworks weren't rigid rules imposed by dominant individuals. They were flexible guidelines that could be adapted to novel circumstances while maintaining core principles that prioritized collective welfare and environmental stewardship. Their philosophical achievements extended to concepts of time, causation, and purpose that enabled them to plan effectively for future challenges and understand the long-term consequences of their actions. This temporal sophistication allowed them to make decisions that benefited not just immediate community members, but future generations and entire ecosystems. The sophistication of their temporal reasoning is evident from the multi-generational nature of their major projects and the sustainable design of their technological systems. They consistently chose approaches that required longer initial investment, but provided greater long-term benefits, indicating that their decision-making processes incorporated extended time horizons and complex benefit-cost analyses. Their understanding of causation enabled them to identify and manipulate the underlying factors that determined environmental conditions, social dynamics, and technological effectiveness. This causal reasoning allowed them to develop interventions that addressed root causes rather than just treating symptoms, creating solutions that were more effective and sustainable. But perhaps most remarkably, they appear to have developed concepts of purpose and meaning that transcended immediate survival needs and encompassed broader questions about existence, identity, and responsibility. These existential insights provided motivation for their remarkable achievements and guided their development of increasingly sophisticated cultural and technological systems. Their exploration of existential questions appears to have included consideration of their relationships with other species, their responsibilities to future generations, and their role in maintaining the health and diversity of their ecosystems. This broader perspective enabled them to create sustainable civilizations that enhanced rather than depleted the natural systems that supported all life. The evidence for their existential sophistication comes from the altruistic behaviors they displayed toward other species and the environmental stewardship practices they maintained even when these activities provided no immediate benefits to their own communities. Their willingness to invest energy and resources in caring for other species and maintaining ecosystem health indicates value systems that recognized intrinsic worth beyond immediate utility. Their existential insights also appear to have included understanding of mortality, continuity, and legacy that influenced their approaches to education, cultural transmission, and environmental management. The consistency with which they invested in long-term projects that would benefit future generations indicates sophisticated understanding of intergenerational responsibility and cultural continuity. The development of their wisdom traditions required not just individual intelligence, but collective processes for developing, testing, and refining philosophical insights over extended periods. Their cultural institutions provided frameworks for philosophical inquiry and debate that enabled communities to explore fundamental questions about existence and meaning while maintaining social cohesion and practical effectiveness. Evidence suggests they had developed systematic approaches to philosophical investigation that included observation, reasoning, discussion, and practical application of insights to real-world challenges. These philosophical methods enabled them to continuously refine their understanding of fundamental principles while adapting their applications to changing circumstances. The sophistication of their philosophical achievements is evident from the remarkable stability and success of their civilizations over millions of years. Their wisdom traditions provided guidance that enabled them to navigate complex challenges while maintaining their core values and cultural identity across vastly different environmental conditions and evolutionary pressures. Their philosophical legacy continues to influence modern understanding of consciousness, meaning, and purpose in biological systems. The insights they developed through millions of years of evolutionary refinement offer alternative approaches to fundamental questions about existence and responsibility that complement modern philosophical traditions. The study of their wisdom traditions reveals principles about the relationship between individual consciousness, collective meaning, and evolutionary success that remain relevant for understanding modern philosophical and ethical challenges. Their success in creating meaningful existence while achieving remarkable technological and social sophistication provides models for addressing contemporary questions about purpose and responsibility. But most profoundly, their philosophical achievements demonstrate that consciousness, meaning, and wisdom can emerge through natural evolutionary processes and provide significant adaptive advantages for complex social species. Their development of sophisticated wisdom traditions challenges assumptions about the uniqueness of human consciousness and suggests that philosophical insight represents a fundamental aspect of advanced biological intelligence. The duck-billed dinosaur wisdom tradition represents the culmination of one of evolution's greatest success stories. From humble beginnings as relatively simple plant-eating dinosaurs, they transformed themselves through millions of years of evolutionary refinement into conscious beings capable of remarkable technological achievement, environmental stewardship, and philosophical insight. Their story demonstrates that intelligence, cooperation, and wisdom can emerge through natural processes and create civilizations that enhance rather than degrade the natural systems that support life. The principles they discovered through evolutionary experimentation continue to inform modern understanding of consciousness, intelligence, and the potential for sustainable relationships between advanced species and their environments. As we reach the end of their extraordinary parade through time, we're left with profound questions about what might have been if their evolutionary journey had continued. The trajectory of their development suggests they were still in the midst of accelerating innovation and cultural refinement when the asteroid impact ended their remarkable civilization. The loss of duck-billed dinosaurs represents one of evolution's greatest tragedies, eliminating not just individual species, but entire categories of biological achievement that had required millions of years to develop. Their extinction terminated evolutionary experiments in consciousness, cooperation, and wisdom that may never be replicated through natural processes. Yet their legacy persists in the fossil record, providing detailed documentation of what's possible when intelligence, cooperation, and environmental stewardship combine through evolutionary processes. Every discovery adds to our understanding of their remarkable achievements and challenges our assumptions about the nature of consciousness and the potential for sustainable civilization. Their parade through scientific understanding continues to reveal new wonders and inspire new questions about the fundamental nature of intelligence, meaning, and purpose in biological systems. They remain among the most instructive examples of evolutionary success and conscious achievement in Earth's entire history. The duck-billed dinosaur parade may have ended 66 million years ago, but their influence on our understanding of life, consciousness, and civilization continues to grow. They serve as both inspiration and instruction for understanding the processes that enable remarkable achievements in biological systems and the potential that exists within evolutionary processes for creating meaning, purpose, and wisdom. Their story reminds us that we are part of an ongoing evolutionary experiment in consciousness and cooperation that continues to unfold around us. The principles they discovered through millions of years of evolutionary refinement remain relevant for addressing modern challenges and creating sustainable relationships between intelligence and environment as we face our own evolutionary challenges and opportunities. The duck-billed dinosaur legacy provides guidance about the potential for consciousness to create positive change while maintaining harmony with natural systems. Their remarkable parade through time continues to march through our understanding, revealing eternal truths about the nature of intelligence, cooperation, and the magnificent potential that exists within the ongoing story of life on Earth. The extraordinary legacy of the duck-billed dinosaurs stands as one of evolution's most remarkable success stories, a testament to what becomes possible when intelligence, cooperation, and environmental wisdom combine through natural evolutionary processes. Their parade through time has finally reached its conclusion in our understanding, but the lessons they provide